Scientists have long debated whether white holes even exist, but the idea of one crossing paths with a black hole is enough to raise some of the most fascinating questions in modern astrophysics. Such a collision would bring together two extreme cosmic objects with entirely different rules, creating a scenario that could reshape how we think about gravity, time, and the very structure of the universe. What if the universe set the stage for one of the rarest and most extreme events in physics? A white hole colliding with a black hole. What would such a clash create? Would it cancel out, explode, or give rise to something entirely new? Before we begin, let us know in the comments below where in the world you're watching from and what time it is there now. Now, join us as we explore what would happen if a white hole would ever collide with a black hole. A black hole is one of the most mysterious objects in the universe. It is so dense and heavy that its gravity is strong enough to trap everything inside it, even light, which is why nothing can be seen escaping from it. The idea of black holes comes from Albert Einstein's theory of general relativity, which showed that when a mass becomes extremely compact, it can collapse into such an object. The outer boundary of a black hole, the point where nothing can get out, is called the event horizon. Once anything crosses this invisible line, it is lost forever. Interestingly, crossing the event horizon does not feel any different at that exact spot. There is no sudden change a traveller would notice. Black holes also behave like perfect black bodies in physics because they do not reflect light at all. Later, scientists discovered that black holes are not entirely silent. According to quantum physics, they should slowly emit very faint energy, called Hawking radiation, named after Stephen Hawking. This radiation looks like the glow of a very cold black body. For black holes formed from stars, this temperature is so incredibly low, measured in billionths of a degree above absolute zero, that it cannot be detected directly with today's instruments. The idea of objects with gravity so strong that even light could not escape goes back much earlier than Einstein. In the 18th century, the English scientist and clergyman John Michel and the French scholar Pierre-Simon Laplace both suggested the possibility of such dark stars. Michel, in a letter written in the year 1784, calculated that if a star had the same density as the Sun but was 500 times larger in radius, then light would not be able to leave its surface. He even pointed out that these invisible stars could still be found by the way their gravity affected nearby visible stars. Laplace, in his book published in the year 1796, also suggested that a star might be so large that it could not be seen, since its light would never escape. At first, many thinkers were excited about this idea, but by the early 19th century, enthusiasm faded. This was because scientists began to understand that light behaves like a wave, and they were not sure how gravity could trap waves. For a while, the concept of dark stars disappeared from serious discussion. Everything changed in the early 20th century. In the year 1915, Albert Einstein completed his theory of general relativity, showing that gravity can indeed bend and influence the path of light. Only a few months later, Karl Schwarzschild, a German physicist, discovered the first exact solution to Einstein's equations. His work showed how a perfectly spherical mass could create the extreme conditions of a black hole. The boundary he described is now called the Schwarzschild radius. Other scientists quickly joined the discussion. In the year 1916, Johannes Droste, a student of the Dutch physicist Hendrik Lorentz, found the same solution and described it in more detail. In the following decades, Arthur Eddington and Georges Lemaitre helped clarify the confusing parts of the theory, showing that the strange singularity at the Schwarzschild radius was not a real physical object, but a feature of the mathematical coordinates. In the year 1931, the Indian physicist Subrahmanyan Chandrasekhar calculated, using the principles of relativity, that stars above a certain mass would collapse without end. This mass limit, now called the Chandrasekhar limit, is about 1.4 times the mass of our Sun. While many scientists of the time, including Eddington, resisted this idea, later work proved Chandrasekhar was right. Stars just above this mass collapse into neutron stars, while those even heavier can collapse all the way into black holes. By the 1950s, physicist David Finkelstein gave the modern interpretation of a black hole as a true region of space where nothing can escape. Still, for many years, black holes were thought to be only mathematical curiosities. It was not until the 1960s that physicists accepted them as natural predictions of Einstein's theory. The first black hole to be identified was Cygnus X1. discovered in the year 1971 by several independent researchers. Since then, astronomers have found many more. Black holes usually form when massive stars reach the end of their lives and collapse under their own gravity. Once formed, a black hole can grow larger by swallowing nearby gas, stars, or even merging with other black holes. Some of the biggest ones, called supermassive black holes, contain millions of times the mass of our Sun. Almost every galaxy, including our own Milky Way, has one of these monsters at its centre. The Milky Way's supermassive black hole, known as Sagittarius A, has a mass of about 4.3 million suns. Astronomers cannot see black holes directly, but they can detect their presence. When gas and dust fall into a black hole, they form a swirling accretion disk, heating up to extreme temperatures and giving off powerful light and radiation. Sometimes, this process powers a quasar, which can shine brighter than an entire galaxy. Stars that pass too close can be ripped apart, producing brilliant flashes before being consumed. Even the orbits of stars around an invisible object can reveal the hidden black hole pulling on them. In the year 1939, the physicists Robert Oppenheimer and George Volkoff built on earlier ideas to predict that neutron stars above a certain mass limit would collapse even further. This limit became known as the Tolman-Oppenheimer-Volkoff TOV limit. Their reasoning followed from the earlier work of Subrahmanyan Chandrasekhar, who had shown that white dwarfs above a certain size would collapse. Oppenheimer and Volkoff concluded that the laws of physics themselves would not be able to prevent some of these massive stars from collapsing all the way into black holes. Their first calculations, which relied on the Pauli exclusion principle, suggested that this upper limit was around 0.7 times the mass of our Sun. Later studies that included the effects of repulsion between neutrons, caused by the strong nuclear force, raised this estimate to somewhere between about 1.5 and 3 times the mass of the Sun. Much later, in the 21st century, the merger of 2 neutron stars observed as the event G-DUT 170817 gave scientists new evidence. This collision likely produced a black hole and allowed researchers to refine the 2V limit to about 2.17 times the mass of the Sun. Oppenheimer and his collaborators also looked at what happens near the boundary of a collapsing star, called the Schwarzschild radius. They suggested that this surface marked the edge of a kind of bubble where, for outside observers, time seemed to stop. To an observer far away, the collapsing star's surface would appear frozen in time right at this boundary. For that reason, they called these hypothetical collapsed stars frozen stars. But for an observer actually falling into the star, time would not stop, showing that perspective made a crucial difference. That same year, 1939, Albert Einstein himself published a paper titled On a Stationary System with Spherical Symmetry, consisting of many gravitating masses. In it, he tried to argue that black holes could not exist, using his own theory of general relativity as a defense. However, only a few months later, Oppenheimer and his student Hartland Snyder presented their famous Oppenheimer-Snyder model in the paper on continued gravitational contraction. Unlike Einstein, they showed how a black hole could form, using Einstein's very own general relativity equations. This was the first modern prediction of black holes in physics, even though the authors did not directly refer to Einstein's recent publication. Nearly 2 decades later, in 1958, the physicist David Finkelstein gave a deeper interpretation of the Schwarzschild surface. He identified it as an event horizon, a one-way boundary across which no signal or influence could escape. Finkelstein even created a new way of describing space-time so that the viewpoint of an observer falling into a black hole could be included. Around the same time, Martin Kruskel had developed a similar idea, though John Wheeler initially did not recognize how important it was. Eventually, the use of Kruskel-Sikaros coordinates gave scientists a powerful tool to understand black holes from several different perspectives. The period from the middle of the 1960s to the middle of the 1970s came to be called the Golden Age of black hole research. During these years, black holes and general relativity moved from being fringe curiosities to becoming central subjects of modern physics. In 1963, Roy Kerr found the exact solution describing a rotating black hole. Just 2 years later, in 1965, Ezra Newman extended this solution to describe black holes that rotate and also carry electric charge. Important work by Werner Israel, Brandon Carter, and David Robinson then gave rise to the famous No Hair Theorem. This theorem stated that a stationary black hole could be fully described by only 3 basic properties: its mass, its spin, or angular momentum, and its electric charge. At first, many scientists thought the strange predictions of black hole theory, especially the appearance of singularities, were simply mathematical oddities caused by overly idealized assumptions. Physicists like Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz even tried to show that singularities could not exist in realistic situations. But in the late 1960s, Roger Penrose and Stephen Hawking used new mathematical methods to prove that singularities were, in fact, an inevitable part of gravitational collapse under general conditions. This was a turning point in physics. Decades later, Penrose was awarded half of the Nobel Prize in Physics in the year 2020 for this work. Stephen Hawking, who had passed away in the year 2018, was widely celebrated for his contributions as well. Observations in astronomy also took major steps forward during this era. In 1967, Anthony Hewish and Jocelyn Bell Burnell discovered pulsars, extremely regular pulses of radio waves coming from space. By the year 1969, it was shown that pulsars were actually rapidly spinning neutron stars. This discovery confirmed that neutron stars were real, not just theoretical ideas, and it spurred a wave of interest in compact objects like neutron stars and black holes. Then, in the early 1970s, further observations from Greenwich in England and Toronto in Canada confirmed that Cygnus X1, an X-ray source first discovered in 1964, was very likely a black hole. It became the first object widely accepted as such. At the same time, important theoretical work was being developed. In the early 1970s, scientists including James Bardeen, Jacob Bekenstein, Brandon Carter, and Stephen Hawking created the framework of black hole thermodynamics. They showed that black holes follow laws closely resembling the laws of thermodynamics, where mass corresponds to energy, surface area corresponds to entropy, and surface gravity corresponds to temperature. Then, in 1974, Hawking made his most famous prediction. Using quantum field theory, he showed that black holes should not be entirely black. They should emit radiation, like a warm object glowing faintly. This effect, now known as Hawking radiation, revealed that black holes slowly lose energy over time. On the 11th of February in the year 2016, the LIGO scientific collaboration together with the Virgo collaboration made a groundbreaking announcement. They revealed the very first direct detection of gravitational waves. This was a historic moment in science because it was also the first time humanity directly observed two black holes colliding and merging into one. A few years later, on the 10th of April in the year 2019, another milestone was achieved. Scientists published the first ever direct image of a black hole and the space immediately around it. This incredible result came from the Event Horizon Telescope, which had made observations in the year 2017 of the enormous supermassive black hole at the centre of the galaxy Messier 87. For the first time in history, people were able to actually see the shadow of a black hole. In more recent years, the European Space Agency's Gaia mission has also contributed to the study of black holes. It detected evidence of a star similar to our Sun orbiting a black hole now known as Gaia BH1, located about 1,560 light-years away, which is roughly 480 parsecs in astronomical terms. Another discovery, Gaia BH2, appears to have a brown dwarf star orbiting it. While scientists have so far only confirmed a few dozen black holes in our Milky Way galaxy, estimates suggest that there may be hundreds of millions of them. Most of these hidden black holes are solitary and silent, giving off no light or radiation. Because of this, they can only be detected indirectly, such as through their gravitational influence on light, a phenomenon known as gravitational lensing. The very phrase black hole also has an interesting history. In December of the year 1967, during a lecture by physicist John Wheeler, a student is said to have suggested the term. Wheeler, appreciating its simplicity and catchy nature, adopted it, and his respected reputation ensured that the phrase spread rapidly. For this reason, many people have credited Wheeler as the person who coined the term. However, the truth is more complicated. Science writer Marsha Bartusiak has shown that the phrase was in circulation before Wheeler's lecture. Physicist Robert H. Dicke, in the early 1960s, reportedly compared such objects to the infamous Black Hole of Calcutta, a prison cell so overcrowded that few who entered ever came out alive. The words black hole were already appearing in print by the year 1963 in Life and Science news magazines. The science journalist Anne Ewing even wrote an article titled Black Holes in Space, published on the 18th of January in the year 1964, reporting on a major meeting of the American Association for the Advancement of Science in Cleveland, Ohio. Now, to understand what a black hole really is, the escape velocity from a black hole is greater than the speed of light itself. In precise scientific terms, a black hole is defined as an object whose mass is squeezed into a radius smaller than its Schwarzschild radius, a mathematical boundary derived from Albert Einstein's equations of general relativity. There is also a famous idea known as the No Hair Theorem. This principle suggests that once a black hole has fully formed and reached stability, it can only be described by three physical properties: its mass, its electric charge, and its spin, or angular momentum. Apart from these three features, a black hole has no other distinguishing qualities. If this conjecture is completely true, then two black holes with identical values for mass, charge, and spin would be indistinguishable from each other. However, physicists are still not entirely sure how perfectly this principle applies in the real universe, and the question remains one of the unsolved puzzles of modern science. These three properties are important because they can be measured from outside the black hole. For instance, a black hole that carries an electric charge will repel other objects with the same charge, just like any ordinary charged particle would. The total mass of a black hole can also be measured from a distance by using a gravitational version of Gauss's law. Similarly, the spin of a black hole can be detected through the effect of frame dragging, where space itself is twisted around the rotating black hole, something described by the lens-Thirring effect. When an object falls into a black hole, all details about its original shape or the way its charge was spread out are lost to outside observers. That information gets smeared evenly across the black hole's event horizon. In physics, this strange behavior is modeled as though the horizon were like a stretched, flexible surface with friction and electrical resistance. This idea is known as the membrane paradigm. Unlike electromagnetism, which is time-reversible and has no resistance at the microscopic level, black holes act more like systems that absorb and dissipate information. Because black holes eventually settle down into a state defined only by mass, charge, and spin, any other information about what fell into them is permanently lost to the outside world. This includes details like the total number of protons or neutrons, which are usually considered nearly conserved in normal physics. This loss of information is so baffling that it is known as the black hole information paradox, one of the deepest mysteries in theoretical physics. The simplest type of black hole has only mass, with no charge and no spin. These are called Schwarzschild black holes, named after Karl Schwarzschild, who discovered this solution in the year 1916. According to Birkhoff's theorem, this is the only spherically symmetric vacuum solution of Einstein's equations. This means that from far away, the gravitational pull of such a black hole looks exactly the same as that of any other spherical object of the same mass. The popular belief that black holes suck in everything is only true very close to the event horizon. At large distances, their gravity is no different from that of an ordinary star or planet with the same mass. There are also more complex solutions describing other kinds of black holes. A non-rotating but electrically charged black hole is described by the Reissner-Nordström metric. A rotating but uncharged black hole is described by the Kerr metric. The most general type of stationary black hole, which has both charge and spin, is described by the Kerr-Newman metric. While black holes can have almost any positive mass, their charge and spin are limited by their mass. If a black hole reaches the maximum possible values for charge or spin, it is called extremal. Theoretical solutions that go beyond this limit exist, but they do not have an event horizon. Instead, they reveal what is called a naked singularity, a point of infinite density exposed to the universe. Because naked singularities would violate our understanding of physics, the cosmic censorship hypothesis argues that such objects cannot form from the collapse of real stars. So far, numerical simulations appear to support this idea. In reality, black holes formed from collapsing stars are expected to have almost no electric charge, since stars are nearly electrically neutral. However, spin seems to be an unavoidable feature. In fact, the Black Hole Candidate System, GRS 1915, plus 105 appears to spin at nearly the fastest rate allowed by physics. Black holes are also grouped by their mass. Their size, measured by the radius of the event horizon, or Schwarzschild radius, is directly proportional to their mass. For spinning or charged black holes, the event horizon is smaller than that of a simple Schwarzschild black hole. In extreme cases, the event horizon can shrink very close to the central singularity itself. The most important feature that makes a black hole unique is something called the event horizon. This is like an invisible boundary in space and time. Once matter or light passes through this boundary, it can only move inward, deeper into the black hole and never back out. Not even light, which is the fastest thing in the universe, can escape from inside this mysterious surface. That is why the event horizon has earned its name. If anything happens within it, no signal, light, or information from that event can ever reach someone outside. To an outside observer, it is as though the event never took place. Albert Einstein's general theory of relativity explains why this happens. According to the theory, every mass bends and distorts space and time around it, like a weight pressing down on a flexible sheet. This bending makes particles and light curve in their paths, always tending to move toward the mass. In the case of a black hole, the distortion becomes so extreme at the event horizon that no possible path exists that can lead away. Everything is trapped inside. A famous thought experiment helps explain what an observer far from a black hole would see. If they watched clocks placed close to the black hole, those clocks would seem to tick more slowly compared to clocks far away. This strange effect is called gravitational time dilation. From the outside, any object falling toward the black hole would appear to slow down as it reached the event horizon, taking an infinite amount of time to fully cross it. The processes happening on that object, its movement, vibrations, or any activity, would all appear to slow down. Even the light coming from it would look increasingly red and faint, an effect known as gravitational redshift. Eventually, the falling object would fade until it completely disappeared. For most objects, this disappearance would happen so fast that to an outside observer, it would vanish in less than a single second. However, an imaginary indestructible observer falling into the black hole would have a very different experience. From their perspective, nothing unusual would happen at the event horizon. Their own clocks would tick normally, and they would cross the horizon in a finite time without noticing any dramatic or special event. This is consistent with Einstein's equivalence principle, which says that no local experiment can distinguish between falling freely in a gravitational field and floating in empty space. The shape, or topology, of the event horizon of a black hole in balance is always spherical. For a black hole that does not spin, called a static or non-rotating black hole, the horizon is perfectly spherical. For a rotating black hole, the horizon becomes slightly flattened at the poles and stretched at the equator, a shape called oblate. At the very center of the simplest type of black hole, the Schwarzschild black hole, there is something even stranger, a gravitational singularity. This is a point where space and time are curved infinitely, where the known laws of physics break down. For a non-rotating black hole, the singularity takes the form of a single point. For a rotating black hole, the singularity stretches into a ring lying in the plane of rotation. In either case, the singularity has no volume, yet it contains all the mass of the black hole. That means its density is infinite. If someone were to fall into a non-rotating Schwarzschild black hole, once they cross the event horizon, their fate is sealed. They might try to delay their fall by using rockets to push away from the singularity, but there is a strict limit, and eventually they would be pulled in. Near the singularity, the gravitational pull would stretch and tear them apart in a process scientists vividly call spaghettification, or the noodle effect, where objects are stretched into long, thin strands. In the end, they would be crushed into the singularity itself, their mass becoming part of the black hole's total. For black holes that either spin, called Kerr black holes, or carry an electric charge, called Reissner-Nordström black holes, the situation is a little different. In these more complex cases, the singularity can, at least in theory, be avoided. When the mathematical solutions are extended, they suggest the bizarre possibility that such a black hole could act like a wormhole, leading to a different region of space and time, or even another universe entirely. These models also predict the possibility of closed time-like curves, meaning that one might loop back into one's own past, raising paradoxes like the famous grandfather paradox. However, physicists generally believe these strange effects are not real, because even the smallest disturbance would destroy such possibilities. Modern theories expect that when quantum physics is fully included, these exotic paths would not exist. The appearance of singularities in Einstein's relativity is a clear sign that the theory breaks down at those extreme scales. At such tiny, dense regions, the effects of quantum physics, governing the behavior of particles, should dominate. But so far, scientists have not been able to unite general relativity with quantum mechanics into a single, complete theory of quantum gravity. It is widely believed that once such a theory is discovered, singularities will disappear from the equations, replaced by something more physically realistic. One interesting alternative proposal is the fuzzball model, developed from string theory. In this model, the different states of a black hole do not contain a sharp event horizon, or a singularity at all. Instead, the black hole is made up of tangled strings of energy. To an observer looking from far away, the average of these states would still appear to behave like an ordinary black hole, as predicted by Einstein's relativity, but deep inside, the structure would be very different. The photon sphere is a strange and fascinating region that exists around a black hole. It forms a perfectly round, invisible boundary where light itself can become trapped. If a photon, which is a particle of light, happens to move along the edge of this boundary, it can circle the black hole in a circular orbit. However, this orbit is not stable. It is a delicate balance, and the slightest disturbance, such as a bit of falling matter or even a tiny gravitational nudge, can throw the photon off its path. When that happens, the photon will either spiral inward, eventually crossing the event horizon and vanishing forever, or be pushed outward, breaking free from the black hole's pull. For a non-rotating black hole, the photon sphere lies at a distance of 1.5 times the Schwarzschild radius, the Schwarzschild radius being the mathematical boundary that defines the size of the event horizon. Light can still escape from the photon sphere, but only under specific conditions. If a beam of light crosses into the sphere while moving inward, it is doomed to be captured. This means that any light an outside observer sees coming from near the photon sphere must have been emitted in the thin region between the photon sphere itself and the event horizon. Things become even more complex with rotating black holes, also known as Kerr black holes. In this case, the size of the photon sphere is not fixed. Instead, it changes depending on two things: the spin of the black hole and the direction in which the photon moves. If the photon orbits in the same direction as the black hole's spin, called a prograde orbit, the photon sphere lies closer to the event horizon. If the photon orbits in the opposite direction, called a retrograde orbit, the photon sphere lies farther away. Rotating black holes also give rise to a remarkable region called the Ergosphere. This is a zone of space-time where it is physically impossible for anything to remain completely still. The reason for this lies in a phenomenon known as frame dragging. According to Einstein's theory of general relativity, when a massive object spins, it drags the very fabric of space-time along with it. For ordinary objects, this effect is tiny and unnoticeable, but around a spinning black hole, the effect becomes extreme. Close to the event horizon, space-time is dragged so powerfully that, to resist being carried along, an object would need to move faster than the speed of light in the opposite direction, which is impossible. The ergosphere is shaped like a squashed sphere. Its inner boundary touches the black hole's event horizon at the poles, but around the equator it stretches much farther outward. Unlike the event horizon, however, the ergosphere does not represent a point of no return. Both matter and radiation can still escape from it. In fact, the ergosphere makes possible a fascinating process known as the Penrose process. In this process, an object that enters the ergosphere can split into two, with one part falling into the black hole and the other escaping with more energy than it originally had. The extra energy comes directly from the black hole's spin, meaning that this process gradually slows the black hole's rotation. An even more powerful variation, called the Blandford-Znajek process, involves magnetic fields and is thought to be responsible for the huge energy output and blazing jets of matter that shoot out from quasars and other active galaxies. In the simpler world of Newton's gravity, an object could orbit a central mass at any distance and remain stable. But Einstein's general relativity paints a different picture. Around a black hole, there exists a special limit called the innermost stable circular orbit, often shortened to ISCO. This orbit marks the closest distance at which matter can circle the black hole without inevitably plunging inward. If an object in the ISCO receives even the tiniest inward push, it will no longer be able to maintain its orbit and will spiral into the black hole. If pushed outward, its fate depends on its energy. It may settle into another orbit, drift farther away, or escape completely. The exact location of the ISCO depends on whether the black hole is spinning. For a non-rotating Schwarzschild black hole, the ISCO lies at a fixed distance, but for a spinning black hole, the ISCO moves inward for matter, orbiting in the same direction as the spin. The last region that astronomers can meaningfully describe before matter vanishes into the black hole is called the plunging region. Beyond this point, stable orbits are no longer possible. Matter can no longer resist the black hole's pull and is forced into a final, unstoppable dive. It rushes inward at speeds approaching the speed of light, crossing the event horizon and disappearing from the observable universe forever. Because black holes are such strange and puzzling objects, scientists once debated for a long time whether they could really exist in the universe, or whether they were only odd and unrealistic outcomes of Albert Einstein's equations of general relativity. Even Einstein himself did not believe black holes would actually form in nature. He thought that as stars or particles collapsed under their own gravity, their rotation, or angular momentum, would keep them stable at some safe distance, preventing them from shrinking endlessly. For many years, this belief caused much of the scientific community working in relativity to dismiss or ignore results that suggested black holes were real. Still, a small group of physicists refused to give up. They argued that black holes were not only mathematical ideas, but real physical objects that could form in the universe. By the end of the 1960s, their arguments convinced most researchers that nothing in the laws of physics prevented the birth of an event horizon, the invisible boundary that marks the point of no return around a black hole. The mathematician Roger Penrose then demonstrated something striking. If an event horizon forms, then Einstein's theory of general relativity, without the help of quantum mechanics, insists that a singularity must also exist deep inside the black hole. Soon after, Stephen Hawking extended this idea further by showing that many solutions of the equations that describe the Big Bang also lead to singularities, even without invoking strange kinds of matter or special fields. Around the same period, the discovery of the Kerr solution, which describes rotating black holes, the No Hair Theorem, and the laws of black hole thermodynamics revealed that black holes, though exotic, were not hopelessly complicated. Instead, their properties could be expressed in surprisingly simple and understandable ways. This made black holes respectable topics of serious research, rather than bizarre oddities. Conventional black holes are thought to form through gravitational collapse, which happens when the inward pull of gravity inside an object becomes stronger than the pressure supporting it from within. In stars, this usually occurs for one of two reasons. Either the star runs out of nuclear fuel and can no longer produce enough energy to resist its own weight, or the star gains additional mass in a way that does not heat its core, enough to restore balance. In both cases, the star's temperature eventually becomes too low to resist gravity, and the star begins to collapse. In some cases, the collapse is halted by what is called degeneracy pressure, a quantum effect that arises from the particles inside the star, such as electrons or neutrons. This pressure can stop the collapse and create a compact object in a new, denser form of matter. Depending on how heavy the remnant core of the star is, the result may be a white dwarf star, a neutron star, or in extreme cases, a black hole. The outcome depends strongly on the final mass of the collapsed remnant after the star's outer layers have been blown away, often in a powerful explosion called a Type II supernova. For example, remnants with a mass greater than about 5 times that of our Sun are usually formed from stars that were originally more than 20 times the mass of the Sun. If the remaining core of a star has more than about 3 to 4 solar masses, a limit known as the Tolman-Oppenheimer-Volkoff limit, then even neutron degeneracy pressure cannot stop the collapse. In that case, the object has no escape. It will inevitably collapse into a black hole. No known physical mechanism, except perhaps an even more exotic quark degeneracy pressure, could prevent this. The gravitational collapse of massive stars is believed to be the main process that creates stellar mass black holes. In the very early universe, however, conditions may have been different. Some stars may have formed with much greater masses, and when these giants collapsed, they could have produced black holes with hundreds or even 1,000 times the mass of the Sun. These objects might have been the seeds from which today's supermassive black holes grew, those enormous black holes that sit at the centers of galaxies. It has also been proposed that, in the young universe, vast clouds of gas could have collapsed directly into black holes without ever forming stars first. Such black holes might have had masses of around 100,000 suns, and could be the ancestors of the earliest quasars, which astronomers have already detected from a time when the universe was only a few 100 million years old at a redshift of about 7. Some promising candidates for such early black holes have indeed been found in deep sky observations. When a star or massive object collapses into a black hole, most of the energy is released very quickly. But from the point of view of a distant observer, the process looks very different. Because of the strange effects of time near strong gravity, an outside observer never sees the final formation of the event horizon. Instead, the collapsing matter appears to slow down as it approaches the invisible boundary. The light from this material becomes weaker and redder, stretched to longer wavelengths until it fades completely from view. To the outside world, it looks as though the material simply freezes just outside the event horizon, never quite crossing it. Gravitational collapse requires extremely high density. In the current age of the universe, such densities are only found inside stars. But in the very early universe, just after the Big Bang, matter was much denser everywhere, making it possible for so-called primordial black holes to form. However, density alone is not enough. For a black hole to form, matter has to clump together rather than being evenly spread out. This means that in the early universe, tiny fluctuations or perturbations in density would have been necessary to start the process of black hole formation. Different models of the early universe predict very different sizes for these fluctuations. Despite the fact that the early universe was incredibly dense, it did not collapse back into a black hole after the Big Bang. This is because the expansion of space was happening even faster than the pull of gravity could act. According to inflation theory, general relativity explains this by allowing for a strange kind of repulsive gravity caused by negative pressure, which overcame the normal attractive pull of matter and energy. This also shows why the equations that describe collapsing stars cannot always be directly applied to the expansion of the universe. While stars collapse under gravity, the universe as a whole was rapidly stretching and expanding, making its behavior very different from that of any single collapsing object. Gravitational collapse, the dramatic process where a dying star's core implodes under its own gravity, is not the only possible way that black holes could be created. In theory, it is also possible for black holes to appear during extremely energetic collisions, provided that the colliding matter reaches a high enough density. By the year 2002, no such events had ever been observed, neither directly nor indirectly, for example, in the form of missing energy during particle accelerator experiments. This absence of evidence suggested that there must be a lower limit to how small or light a black hole can be. According to theoretical physics, this limit is believed to sit near the so-called Planck mass, an unimaginably tiny scale at which the laws of quantum mechanics are expected to overpower the predictions of Einstein's general relativity. If this is true, then the creation of black holes is well beyond the reach of any earthly or near-Earth processes, no matter how powerful. Yet, some bold developments in the field of quantum gravity have hinted at a surprising alternative. The minimum black hole mass might be much smaller than the Planck mass. Certain ideas, such as brane-world models, propose that the threshold could be as low as 1 tera-electron-volt divided by the speed of light squared. If such theories were correct, then microscopic black holes might form naturally when ultra-high energy cosmic rays slam into the Earth's atmosphere. They could even be produced in machines such as the Large Hadron Collider at CERN. Still, these scenarios are highly speculative, and most experts remain unconvinced that microblack holes could actually appear this way. Even if they did, the theory predicts they would evaporate almost instantly, within about 10 to the power of negative 25 seconds, disappearing before they could pose any danger to our planet. Once a black hole does come into existence, it can grow by feeding on matter. It constantly pulls in interstellar gas, dust, and any material that ventures too close. This feeding process is thought to be one possible path by which the gigantic supermassive black holes at the centers of galaxies might have formed. The exact details of their growth remain one of the great unsolved questions of modern astrophysics. Something similar may also explain the formation of intermediate mass black holes that are sometimes found in globular star clusters. Another important growth mechanism is merging. Black holes can collide and merge not only with stars but also with each other. This merging process is believed to have played a crucial role in the early growth of supermassive black holes, which may have begun as smaller objects that gradually combined into truly colossal ones. In the year 1974, the physicist Stephen Hawking made one of the most groundbreaking predictions in astrophysics. Black holes are not completely black. Instead, they emit faint radiation, now famously called Hawking radiation. By applying the rules of quantum field theory to the curved space around a black hole, Hawking showed that black holes should release particles in a spectrum identical to that of a perfect black body. Since his discovery, many researchers have confirmed the mathematics of his result using different methods. If Hawking was right, then black holes should slowly shrink over time as they lose energy in the form of photons and other particles. The temperature of this so-called Hawking radiation depends on the mass of the black hole. For a Schwarzschild black hole, the larger the mass, the cooler it becomes. This means that small black holes radiate more strongly, while massive ones radiate very weakly. For instance, a stellar black hole with a mass equal to our Sun would have a Hawking temperature of about 62 nanokelvins, much colder than the 2.7 Kelvin cosmic microwave background that fills the universe. Because of this, stellar and larger black holes actually absorb more energy from the surrounding cosmic background than they emit, causing them to grow instead of shrink. To evaporate instead of growing, a black hole would need to be smaller than the Moon, with a diameter of less than 1/10 of a millimeter. Such tiny black holes would be incredibly hot and would radiate rapidly. A black hole with the mass of a car, for example, would measure only about 10 to the power of negative 24 meters across and would evaporate in roughly 1 nanosecond. During that fleeting instant, it would shine with a brightness over 200 times greater than the Sun. Even smaller black holes would vanish even faster. One with a mass of only 1 tera electron volt per speed of light squared would be gone in less than 10 to the power of negative 88 seconds. At such minuscule scales, the effects of quantum gravity would become extremely important, and while some theories have speculated that they might stabilize these tiny black holes, current evidence does not support this idea. For astrophysical black holes, the ones formed from stars or larger structures, the Hawking radiation is expected to be so faint that it is essentially undetectable from Earth. An exception might occur during the final instant of evaporation of very old, primordial black holes, when they could release a violent burst of gamma rays. Astronomers have searched for such flashes but have found none, setting strong limits on the number of low-mass primordial black holes that might exist. NASA's Fermi Gamma Ray Space Telescope, which was launched in the year 2008, continues to scan the skies for these signals. If Hawking's prediction holds true, then even the largest black holes will eventually disappear. A black hole with the mass of our Sun would take about 10 to the power of 64 years to evaporate, but this evaporation would only begin once the temperature of the cosmic microwave background had cooled below the black hole's own temperature. Supermassive black holes are far more durable. One with a mass of 100 billion suns would evaporate in about 2 times 10 to the power of 100 years. And in the farthest reaches of time, even black holes formed during the collapse of entire superclusters of galaxies, possibly reaching masses of 100 trillion suns, would fade away after around 10 to the power of 1006 years. By their very nature, black holes are dark and silent. They do not shine or give off light that we can see, nor do they emit any form of electromagnetic radiation that astronomers can normally detect. The only exception would be the faint and still unproven Hawking radiation, which exists only in theory. Because of this, scientists cannot usually see black holes directly. Instead, they must rely on indirect clues, watching how black holes affect their surroundings, such as how they tug on nearby stars or bend light with their intense gravity. A major breakthrough in this search came through the Event Horizon Telescope, often called the EHT. This project is not a single telescope, but rather a global network of radio observatories spread across several continents. Working together, they create what is essentially an Earth-sized telescope, powerful enough to study black holes directly. The EHT focuses on the regions right at the edge of a black hole's event horizon, the invisible boundary where nothing, not even light, can escape. In the month of April in the year 2017, the EHT began a historic observing campaign. It targeted the giant black hole sitting at the centre of the galaxy Messier 87, which is located in the Virgo cluster of galaxies. Over the course of 10 days, 8 radio observatories, spread across 6 mountains and 4 continents, combined their efforts to collect data. 2 years later, in April of the year 2019, the EHT revealed its results to the world, the very first image of a black hole. This now famous picture did not show the black hole itself, because the black region swallows all light and appears as a shadow. Instead, what was visible was a glowing ring of hot gas orbiting right at the edge of the event horizon. The gas appeared in fiery shades of orange and red, glowing brighter where matter was being heated to extreme temperatures as it circled the black hole. On the 12th day of May in the year 2022, the EHT made another announcement of great importance. It released the first image of Sagittarius A, the supermassive black hole that lies at the very centre of our own Milky Way galaxy. This image showed the same ring-like shape and dark central shadow that had been seen in Messier 87's black hole, confirming predictions of Einstein's theory of general relativity. However, capturing this picture was far more difficult than the earlier one. Sagittarius A is more than 1,000 times smaller and less massive than the black hole in Messier 87, which made the imaging process much more challenging. Its environment is highly unstable, and turbulent plasma clouds between Earth and the galactic centre blurred the signal. Despite these obstacles, the EHT succeeded in producing the remarkable image, though it appeared somewhat blurred. One striking feature in both black hole images is that the lower half of the ring looks brighter. This effect is explained by what is known as Doppler beaming. Matter orbiting the black hole at nearly the speed of light appears brighter when it is moving toward us and dimmer when it moves away. In fact, the gas around these black holes must be rotating at extraordinary speeds, over 1,000 kilometers every second, or more than 2 million miles per hour. Only at such extreme speeds can the orbiting matter resist being pulled straight into the black hole's crushing gravity. The bright pattern revealed by the EHT also showed that Messier 87's black hole is being viewed almost edge-on, with its disk of material rotating clockwise. The powerful gravity of black holes also bends light in dramatic ways. This effect, known as gravitational lensing, allows us to see parts of the black hole's disk that would normally be hidden behind it. In other words, the light from the far side of the disk curves around the black hole and reaches our eyes, creating the illusion that we can see the entire glowing ring all at once. Even before these historic images, the Event Horizon Telescope had already made progress. In the year 2015, it detected magnetic fields swirling just outside the event horizon of Sagittarius A. These fields were complex, with some lines neatly ordered while others were tangled. Theoretical physics had long predicted that black holes should have such magnetic fields, and the EHT's findings confirmed this prediction. In April of the year 2023, another milestone was reached when astronomers presented for the first time an image that showed both the shadow of the Messier 87 black hole and the gigantic jet of high-energy particles it blasts into space. But the story of proving black holes' existence does not stop there. On the 14th day of September in the year 2015, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, made history. It detected the first ever direct signal of gravitational waves, tiny ripples in the fabric of space-time itself. These waves were created when two black holes collided and merged into one. One of the black holes weighed about 36 times the mass of our Sun, while the other had about 29 times the Sun's mass. The signal from their merger confirmed that black holes are real and provided the most convincing evidence yet of their existence. Just before the merger, the two black holes were only about 350 kilometers apart, a distance just 4 times larger than the theoretical Schwarzschild radius for objects of that mass. The only explanation for such compact and massive objects was that they were indeed black holes. Even more fascinating, the LIGO signal included what is called the ring down, a fading echo produced as the newly formed black hole settled into a stable shape after the collision. This ring down offered the clearest direct sign of a black hole ever recorded. By carefully analysing the frequency and the rate at which the signal faded, scientists were able to calculate the final black hole's mass and spin. These results matched perfectly with predictions made through advanced computer simulations. This event also provided the first clear evidence that pairs of stellar mass black holes exist, and that some of them can be as heavy as 25 times the mass of the Sun or more. Since that discovery, LIGO and its partner observatories have gone on to detect many more gravitational wave signals from other black hole mergers, turning the once theoretical study of black holes into a direct and ongoing field of observation. The movements of stars close to the very centre of our Milky Way galaxy give astronomers some of the strongest evidence that a gigantic, invisible object lies there, a supermassive black hole. Since the year 1995, scientists have carefully tracked the paths of about 90 stars that orbit around a hidden object sitting right at the same location as the strong radio source known as Sagittarius A star. By studying how these stars move and comparing their orbits to those predicted by Kepler's laws of motion, astronomers realized, in the year 1998, that an object with a mass about 2,600,000 times that of our Sun must be squeezed into a region only about 0.02 of a light-year across to create such motions. Not long after, one particular star named S2 completed a full orbit around this mysterious object. With this extra data, scientists improved their calculations. They now estimate that the hidden object has a mass of about 4,300,000 suns, packed inside a region less than 0.02 of a light-year across. That is unimaginably dense. The upper size limit of this object is still too large to prove if it is smaller than its Schwarzschild radius, the size of the event horizon, but all the evidence strongly points to it being a supermassive black hole. No other known process in the universe could squeeze so much mass into such a tiny volume of space. There are even hints that this object has an event horizon, a feature unique to black holes. Because of the conservation of angular momentum, gas that falls into the powerful gravitational grip of a black hole or any very massive object does not fall straight in. Instead, it swirls into a flat disc-like shape around the object. These swirling structures are called accretion discs. Artists often draw black holes as flat, featureless circles that block out the part of the disc hidden behind them. But in reality, the extreme gravity around a black hole bends light in such a way that the whole disc would appear warped and distorted, creating a far stranger image than those drawings. Inside these disks, the gas rubs against itself, creating friction. This friction pushes angular momentum outward, allowing the gas to spiral further inward. As it falls, the gas releases enormous amounts of gravitational energy, heating up to extraordinary temperatures. When the central object is a neutron star or a black hole, the inner regions of the disk spin so fast that they heat up enough to glow with X-rays, producing some of the brightest signals astronomers can detect. Accretion is also one of the most efficient energy-making processes known. Up to 40% of the material's mass can be converted into energy, compared to less than 1% in nuclear fusion, the process that powers ordinary stars. Sometimes these systems produce narrow, powerful streams of particles called relativistic jets, which shoot out along the poles at nearly the speed of light. The exact mechanism behind these jets is still a mystery, partly because astronomers do not yet have enough data. But what is clear is that many of the universe's most energetic events, such as quasars and active galactic nuclei, are powered by matter falling into supermassive black holes. Smaller systems called X-ray binaries provide another way to study black holes. In these systems, one star is a normal star while the other is a compact object, such as a neutron star or a black hole, which pulls in gas from its companion. As the gas falls in, it glows brightly in X-rays. If astronomers detect signals coming directly from the compact object, it cannot be a black hole, because black holes emit no such signals. But if no such signals are seen, the object might still be a neutron star. By studying the orbit of the companion star, astronomers can estimate the mass of the compact object. If the mass is greater than the maximum limit for a neutron star, the Tolman-Oppenheimer-Volkoff limit, then the only explanation is that the object is a black hole. The first strong candidate for a black hole was discovered this way. It was called Cygnus X1 and was found in the year 1972 by Charles Thomas Bolton, Louise Webster and Paul Murdin. At the time, there was still some doubt because the companion star was unusually massive, making measurements less certain. Today, better candidates are found in a class of systems known as soft X-ray transients. In these systems, the companion star has a much lower mass, which allows for more accurate measurements of the black hole's mass. These systems only flare up and produce bright X-rays for a few months once every 10 to 50 years. During their quieter phases, known as quiescence, the accretion disk becomes faint, allowing astronomers to observe the companion star more clearly. One of the best examples of such a system is called V404 Cygni. Astronomers have also witnessed stars being torn apart by the immense tidal forces near supermassive black holes in dramatic events called tidal disruption events. Some of the shredded material forms an accretion disk around the black hole, which then lights up in radiation that telescopes can detect. In November of the year 2011, astronomers reported the first direct observation of a quasar's accretion disk surrounding a supermassive black hole, confirming a long-standing theory. The disks of gas and dust that swirl around compact objects like black holes, known as accretion discs, sometimes produce flickering X-ray emissions. These flickers appear at specific frequencies and are called quasi-periodic oscillations. Scientists believe that these signals come from material moving very close to the inner edge of the disk, at the point known as the innermost stable circular orbit. Because the frequency of these oscillations depends directly on the mass of the compact object, they provide astronomers with an alternative way to estimate the mass of black hole candidates. Astronomers also use the phrase active galaxy to describe galaxies that show unusual features. These galaxies often emit unusually strong radiation, such as powerful radio waves or distinctive spectral lines in their light. Studies, both theoretical and observational, suggest that the extraordinary energy of these active galactic nuclei, or AGN, comes from the presence of supermassive black holes. These giant black holes are millions of times more massive than typical stellar black holes, and in some cases they can even reach billions of times the mass of our Sun. The standard model of AGN includes three main parts. At the centre lies a supermassive black hole. Around it spins a bright and hot accretion disk of gas and dust, and shooting out from the poles of this disk are two enormous jets of energy and particles. Although supermassive black holes are thought to be at the core of nearly all AGN, astronomers have been able to carefully study and measure only a few galaxies where these central objects are suspected to exist. Some of the most famous examples of galaxies believed to harbour supermassive black holes are the Andromeda Galaxy, Messier 32, Messier 87, NGC 3115, NGC 3377, NGC 4258, NGC 4889, NGC 1277, OJ 287, APM 08, 279 + 5255, and the Sombrero Galaxy. Today, it is widely accepted that the centres of nearly all galaxies, not just the unusually active ones, contain supermassive black holes. One of the strongest pieces of evidence is a close connection between the mass of a galaxy's central black hole and the way stars move in the galaxy's bulge. This relationship, called the M-sigma relation, suggests that the growth of a galaxy and the growth of its black hole are deeply connected. Another way scientists test whether a mysterious object is really a black hole is by observing the effects of its powerful gravity. One well-known effect is called gravitational lensing. Just as a glass lens bends light, the warped spacetime around a massive object can bend the path of light rays. In weak gravitational lensing, the bending is tiny, just a few arcseconds. In microlensing, the light source cannot be seen separately, and instead the observer notices a temporary brightening. At the very end of the 20th century, astronomers reported the first 3 possible black hole detections using microlensing. Much later, in January of the year 2022, astronomers announced the first confirmed microlensing event caused by an isolated black hole. Another possibility for observing the effects of a black hole's gravity is to study stars that orbit around it. For example, several stars near Sagittarius A, the black hole candidate at the centre of our own Milky Way galaxy, are being observed for this very reason. While the case for supermassive black holes is very strong, the situation is more complex for stellar mass black holes. The standard model assumes that there is an upper mass limit for neutron stars, and that any object with more mass than this must collapse into a black hole. However, the behaviour of matter at extremely high densities is still not fully understood. Some scientists think there may be exotic forms of matter that could produce other strange objects instead of black holes. These include hypothetical quark stars, made of free quarks at very high densities, and Q stars, predicted by some versions of supersymmetry. Other theories, which go beyond the standard model of particle physics, suggest the existence of even more exotic objects such as prion stars, made of particles more fundamental than quarks and leptons. Although such objects could, in theory, explain certain observations of black hole candidates, the rules of Einstein's theory of general relativity still place an upper limit on how massive these stars could be. One curious fact about black holes is that their average density inside the Schwarzschild radius decreases as their mass increases. This means that supermassive black holes are actually much less dense than stellar mass black holes. For instance, A black hole with a mass of 100 million suns would have an average density similar to that of water. Because of this, the physics behind the formation of supermassive black holes is relatively easier to understand, and alternative explanations for their existence usually turn out to be much less convincing. For example, one might imagine a huge cluster of dark objects gathered at a galaxy's center instead of a single supermassive black hole. However, such clusters are unstable and would not survive long enough to explain the observations. Over the years, theorists have also suggested a few exotic objects that might mimic the behavior of black holes while being fundamentally different in nature. These include the Grava star, the black star, the related nest star, and the dark energy star. Each of these ideas tries to explain the same observations that point toward black holes, but with a different underlying mechanism. In the theory of general relativity, a white hole is described as a strange and purely theoretical region of space and time linked to a singularity. Unlike a black hole, which nothing can escape from once it crosses the event horizon, a white hole is thought to work in the exact opposite way. Nothing from the outside can ever enter it, yet energy, matter, light, and even information can burst outward from it. In this sense, it is the mirror image of a black hole. White holes appear naturally in the mathematical solutions of what physicists call eternal black holes. In these solutions to the Einstein field equations, there exists both a black hole region in the future and a white hole region in the past. However, such a white hole region does not exist for the black holes that we believe form in the real universe through the process of gravitational collapse. Furthermore, no physical process has ever been observed, nor even clearly predicted, that could actually create a white hole in nature. For now, they remain entirely hypothetical. Physicists also study supermassive black holes, which are predicted to sit at the center of nearly every galaxy. These enormous black holes may even play a central role in the very formation of galaxies themselves. The famous physicist Stephen Hawking, along with other researchers, suggested that such supermassive black holes could in theory give rise to supermassive white holes, although this idea is still speculative. Just like black holes, white holes are thought to have measurable properties such as mass, charge, and spin, or angular momentum. They exert a gravitational pull just like any other massive body in the universe. However, the difference is that any object falling toward a white hole would never actually cross its event horizon. In certain mathematical models, such as the so-called maximally extended Schwarzschild Solution, the white hole event horizon of the past smoothly becomes a black hole event horizon in the future. This means that objects falling toward it would eventually find themselves at the horizon of a black hole instead. To help picture this, think of gravity itself. On the surface of a planet or star, the pull of gravity has a maximum strength at the surface. But in the case of a black hole or white hole, there is no true surface. Instead, gravity grows stronger and stronger as you move inward toward the singularity, without ever reaching a final limit, because the singularity is not a surface, but a boundary of infinite density. In the world of quantum mechanics, black holes do not stay completely dark. According to Hawking's theory, they emit what is now called Hawking radiation, and in certain conditions, a black hole can even reach a state of thermal equilibrium with the radiation around it. Hawking pointed out that such a state is symmetric with respect to time. If you reverse time in such a situation, a black hole in equilibrium would turn into a white hole in equilibrium. Both would absorb and release energy in equal balance. This argument suggested that black holes and white holes could be seen as reciprocal objects. The energy emitted by a black hole through Hawking radiation might correspond to the natural outward emission of matter and energy from a white hole. Later, Hawking's semi-classical reasoning was echoed in more advanced approaches, such as AD-CFT correspondence in quantum theory. In this framework, a black hole in what is known as anti-de Sitter space can be described in terms of a thermal gas within a gauge theory, and when time is reversed, it looks essentially the same. In the early years of the 20th century, during the 1930s, the brilliant physicist Robert Oppenheimer and his colleague Hartland Snyder put forward a daring new idea while studying Albert Einstein's equations of general relativity. These equations are the very foundation of modern physics, describing how the fabric of space and time bends and curves in the presence of massive objects like stars and planets. Oppenheimer and Snyder suggested the possibility of something even stranger than black holes, objects called white holes. While black holes are formed from the collapse of dying stars and act like one-way traps from which nothing, not even light, can escape. White holes represent the complete opposite. They were imagined as cosmic birthplaces, regions where space and time do not collapse inward, but instead burst outward, potentially giving rise to new universes. At their centre, unlike black holes which crush everything into a singularity, white holes avoid this fate by passing through a mysterious transition zone. In this zone, the usual laws of Einstein's equations break down because of quantum effects, and from it, space and time emerge anew, carrying the structure of a white hole interior. This bold possibility had already been hinted at by another great thinker, John Lytton Singh. The idea did not stop there. In the year 1964, the Russian cosmologist Igor Novikov formally raised the possibility of white holes, and this concept was further developed by Nikolai Kardashev. According to Einstein's equations, white holes naturally appear in a mathematical solution known as the maximally extended Schwarzschild metric. This describes an eternal black hole that has no charge and no spin. The term maximally extended means that space and time in this solution cannot simply end at an edge. They must continue indefinitely unless interrupted by a singularity. When physicists examined this solution carefully, they realized something fascinating. In addition to the familiar black hole interior, there must also exist a white hole interior. This allowed them to imagine the paths of particles in new ways. For instance, particles falling into a black hole cross the event horizon and eventually hit the singularity, while particles leaving a white hole cross outward through its horizon, appearing to distant observers as if they had been moving outward for an eternity. To someone watching from the outside, black holes and white holes seem eternal. From this perspective, particles can always be seen falling inward toward the black hole, or rushing outward from the white hole no matter when you look. This creates a strange symmetry between collapse and expansion, past and future. The picture grows even stranger. The maximally extended space-time does not contain only one universe, but two separate exterior regions, two universes connected by the structure of the solution. In this framework, particles can fall from either universe into the same black hole interior, and light from one universe could, in principle, be seen by an observer who entered from the other. Likewise, particles escaping from the white hole interior could emerge into either universe. All of these regions, two interiors and two exteriors, can be represented beautifully in space-time diagrams that use Kruskal-Shekera's coordinates. If one chooses a surface of constant time and draws an embedding diagram showing how space is curved at that moment, the picture looks like a tube or throat connecting the two universes. This structure is known as an Einstein-Rosen Bridge, or more popularly a Schwarzschild wormhole. Depending on how the surface is chosen, the wormhole may connect two black hole horizons or two white hole horizons. However, despite its appearance, this bridge cannot be used to travel between universes. The reason is simple. No one can enter a white hole from the outside, and anyone who crosses into a black hole horizon is doomed to hit the singularity. It is important to note that this is all based on an idealized mathematical black hole that has existed forever. Real black holes, which form from collapsing stars at particular moments in cosmic history, require a different description. When astrophysicists add the collapsing stellar matter into the equations, the white hole region of the solution disappears. Yet, because the equations of general relativity are symmetric in time, that is, they work the same if you reverse the direction of time, there must also exist the mirror image of a black hole. This time-reversed version would be a white hole that has existed since the birth of the universe itself. Such an object would continually emit matter until, at some final moment, it exploded and vanished. Even though these objects are perfectly possible on paper, most physicists remain skeptical. White holes are considered far less likely to exist than black holes, since no natural process seems capable of creating them. They could only exist if they were somehow present in the very first conditions of the Big Bang, and even if they did exist, theory predicts they would be extremely unstable. The tiniest bit of matter falling toward a white hole would ruin its delicate balance, preventing its explosion and trapping the emitted matter forever inside its gravitational grip. When scientists explore the strange mathematics of black holes, they discover that not all solutions look the same. Depending on the type of black hole being studied, different kinds of white holes can appear in the equations. For example, in the case of the simplest type, known as a Schwarzschild black hole, a path of light or matter that emerges from a white hole seems to originate directly from its hidden gravitational singularity, a point of unimaginable density where normal physics breaks down. But when the black hole is more exotic, such as one carrying an electric charge, called a Reissner-Nordstrom black hole, or one that spins rapidly and possesses angular momentum, called a Kerr black hole, then the story becomes even stranger. In those cases, the white hole is not simply a source in our universe, but rather the exit door of a black hole that exists in another universe entirely. This bizarre connection between the two is what physicists call a wormhole. Yet, in both of these scenarios, one thing remains clear. No traveller or particle can enter the inside of a white hole. Its interior is completely cut off. We can only watch what might spill out of it, never step inside to explore. And because of this, a white hole behaves in a way that is impossible to predict. Physicists call such situations non-deterministic, meaning the laws of physics cannot foretell exactly what will happen next. Another example of such unpredictability is something called a naked singularity, a point of infinite density that is not hidden behind an event horizon. Unlike a white hole, however, a naked singularity has no forbidden region of space around it. In some ways, the Big Bang itself can be thought of as a naked singularity that appeared in the void of space. But while it shares similarities, it does not truly fit the definition of a white hole. Black holes, in contrast, have a much clearer story. They are born from the death of massive stars, when the core of the star collapses under its own gravity and squeezes into a black hole. This process is not eternal. Stars live, die, and collapse, so the black hole that follows has a beginning. And since white holes show no sign of having a birth process, they seem far more mysterious. For a white hole to exist, it would either need a special process to form it naturally, or it must have been present since the very beginning of the universe. Neither idea is convincing. Astronomers have never found a physical mechanism that could create a white hole, and assuming that one simply appeared at the moment of creation would mean the universe started with extremely special conditions, with no good reason for why it should have been so. In earlier decades, when scientists first noticed quasars, incredibly bright objects that shine so intensely they can be seen from billions of light years away, many thought they might be powered by white holes, or even by some new process of matter continuously being created. Later discoveries, however, revealed a simpler truth. Quasars are powered by gigantic accretion discs of hot matter, swirling around supermassive black holes at the hearts of galaxies. This explanation matched all the observations perfectly, and the white hole idea was set aside. Still, some researchers in the late 1980s suggested a fascinating twist. Maybe when a black hole forms, something like a Big Bang occurs deep inside it. In that hidden core, a new universe could be born, expanding outwards while hidden from its parent universe. In this picture, every black hole might give rise to a baby universe, and from the perspective of that new universe, the parent appears as a single shining white hole. This idea fits nicely with the Einstein-Cartan-Siama-Kibble theory of gravity, which adds extra features to Einstein's general relativity. In this theory, gravity is influenced not only by mass and energy, but also by the spin of particles. At extremely high densities, this spin can create a repulsive effect, preventing matter from collapsing into a true singularity. Instead, the collapsing matter bounces back, forming a bridge known as an Einstein-Rosen Bridge. On the other side of that bridge, a new universe begins to expand. From within that baby universe, the original parent universe would appear as its only white hole. In this view, our own Big Bang may have been not a singular explosion but a smooth big bounce, the rebirth of space and time from a collapsing universe before ours. In the early years of the 21st century, new cosmological models continued to play with this idea. In the year 2003, scientists Joel Smoller and Blake Temple proposed shockwave cosmology, in which the Big Bang is seen as an explosion happening inside a black hole, with the universe expanding outwards as a white hole. In 2012, another paper argued that the Big Bang itself was a white hole, describing it as a small bang, in which all the matter of the universe was expelled in a single instant, like one enormous pulse. This idea even suggested that certain mysterious gamma-ray bursts could be linked to white holes appearing and vanishing in an instant. Despite these imaginative proposals, the mystery remains. While black holes are well understood as the product of collapsing stars, no known process creates white holes. Scientists have put forward several possibilities. Perhaps white holes are connected to black holes through wormholes. Perhaps they are unstable and collapse almost immediately into black holes. In the year 2006, astronomers Alon Retter and Shlomo Heller even suggested that an unusual gamma-ray burst, known as GRB 060614, might have been the first observed white hole. Later, in the year 2014, 3 physicists, Madriz Aguilar, Moreno and Bellini, suggested that the Big Bang itself might have been the result of a supermassive white hole explosion occurring in a strange 5-dimensional vacuum. Other thinkers have even speculated that white holes are simply the time reverse of black holes, existing not as places where things fall in, but as places where things only pour out. In the 21st century, almost all astronomers and physicists agree that white holes are not real objects in the universe. Instead, they are treated as mathematical curiosities, strange solutions hidden in the equations of relativity, with no evidence of existing in the cosmos around us. Could white holes even exist? That question has fascinated scientists, dreamers, and storytellers alike for more than a century. It touches on the deepest mysteries of the universe, mysteries that link time, space, matter, and the strange invisible rules that hold reality together. A white hole, in the most basic sense, is thought of as the exact opposite of a black hole. While a black hole pulls everything into it with a gravity so strong that not even light can escape, a white hole would do the reverse. It would spit out matter and light but would never allow anything to fall inside. To picture it simply, think of a black hole as the ultimate cosmic trap and a white hole as the ultimate cosmic fountain. The two are mirror images, like night and day, or breathing in and breathing out. The idea of white holes first grew from mathematics rather than from any telescope view of the sky. In the early 20th century, Albert Einstein's equations of general relativity gave humanity a new way to see gravity. Instead of imagining gravity as an invisible force pulling at objects, Einstein showed that massive things like stars and planets actually bend the very fabric of space and time around them. That bending makes smaller objects move along curved paths, just as a marble rolls along the dip of a stretched rubber sheet when you place a heavy ball in the middle. Einstein's equations were beautiful but also strange, because they suggested that extreme shapes of space-time could exist, shapes far beyond what ordinary experience on Earth could prepare anyone to imagine. One of those shapes was the black hole. Karl Schwarzschild, a German physicist fighting in the First World War, found the first exact solution to Einstein's equations in the year 1916. His solution described a point of infinite density called a singularity, surrounded by a spherical boundary known as an event horizon. Anything that crossed the event horizon could never escape. That was the first mathematical black hole, though the name itself was not coined until the 1960s by the American physicist John Wheeler. But when mathematicians studied these solutions more carefully, they discovered something curious. The same equations that described a black hole also allowed for a mirror solution, a kind of time-reversed black hole. Instead of sucking in matter, this mirrored object would only expel it. This became known as a white hole. It was as if the equations of general relativity contained not only a doorway leading inward forever, but also a doorway leading outward forever. This led to a debate between theory and observation. On paper, white holes made sense. They were mathematically permitted, just as black holes were. But while black holes had many lines of evidence to support them, such as the X-ray glow from matter heating up as it spirals inward, or the bending of light near massive objects, white holes had none. No telescope had ever spotted a star being blasted apart by a fountain of matter with no source. No observatory had ever seen light and radiation gushing outward from a point in space where nothing could be approached. For all their mathematical neatness, white holes seemed like ghostly ideas without proof in the real sky. Scientists asked, could white holes even exist, or are they just artifacts of equations? To understand why this is such a hard question, one must think about time itself. In Einstein's theory, the laws of physics do not prefer one direction of time over the other. If you watch a movie of 2 billiard balls colliding and then play it backwards, the physics looks perfectly reasonable. But in real life, time does seem to flow in one direction. Eggs break but do not unbreak, smoke spreads but does not reassemble, and people grow older but never younger. This is called the arrow of time, and it is tied to the increase of entropy, which is the measure of disorder in the universe. A black hole fits with this arrow of time because things fall into it and do not come out again, adding to the total disorder of the cosmos. But a white hole would seem to run against the grain. It would spew out matter that appears from nowhere, neatly reversing the process. That is one of the reasons why many physicists doubt that white holes can really exist in nature. Still, imagination has power in science. Some researchers have suggested that maybe what we call the Big Bang, the beginning of the universe almost 14 billion years ago, was itself a kind of white hole. In this view, all the matter, energy, and space of the cosmos suddenly erupted outward from an initial singularity. Just as nothing can enter a white hole, nothing could have existed before the Big Bang. This comparison does not prove anything, but it shows how the idea of white holes stirs the mind to picture beginnings as well as endings. Other scientists have asked if a white hole might be connected to a black hole by a tunnel through space-time. This tunnel is what is usually called a wormhole, or in more formal terms, an Einstein-Rosen Bridge, after the two physicists who described it in the 1930s. If such a tunnel exists, then matter falling into a black hole could, in theory, emerge from a white hole somewhere else, maybe even in another universe. It would be like going into a cave and finding yourself suddenly walking out of a mountain on the other side of the world. The difficulty, though, is that wormholes, if they exist, would be highly unstable. They would collapse faster than anything could travel through them, unless some exotic form of negative energy held them open. To this day, negative energy of the required kind has never been found in nature, although quantum physics hints at its possibility in tiny amounts. Because the debate is ongoing, researchers often look for ways to test the idea of white holes. Could an event in the sky reveal one? Some have wondered if certain mysterious flashes of energy called gamma-ray bursts might be signs of white holes. Gamma-ray bursts are the most powerful explosions ever recorded by instruments, lasting from fractions of a second to several minutes. They outshine entire galaxies for a brief time. Most are believed to be caused by collapsing stars forming black holes or by neutron stars smashing together. But a few bursts do not fit these models neatly. A minority of physicists have proposed that perhaps those unexplained flashes could be small white holes popping into existence for a short moment, releasing their energy and then vanishing. This idea remains speculative, but it shows that the conversation between theory and observation is still alive. It is important here to remember the role of imagination in science. Many discoveries began as pure mathematics or strange ideas that seemed impossible at first. When black holes were first described, even Einstein himself did not believe they would exist in reality. They were seen as odd quirks of equations. Yet today we have photographed the shadow of a black hole in the galaxy M87 using the Event Horizon Telescope, and we have detected the ripples in spacetime caused by two black holes colliding, using the LIGO and Virgo observatories. If black holes went from theory to observation in a century, could white holes someday make the same journey? That remains uncertain. In the debate, some scientists argue that the laws of physics might actively forbid white holes from forming. For example, if a star collapses under its own weight, it can form a black hole. But there seems to be no natural process that could run in reverse to make a white hole. Nature tends to allow processes that increase entropy, not decrease it. So, unless there was some hidden mechanism at the birth of the universe, white holes may simply be impossible. Others, however, hold on to the possibility. They point out that quantum mechanics, the strange set of rules governing atoms and particles, might interact with general relativity in ways we do not yet understand. Our knowledge is incomplete, especially when it comes to the extreme conditions near singularities. It may be that once quantum gravity is fully understood, the door to white holes might open in a new way. To make these abstract thoughts more vivid, one can borrow comparisons from the animal world. Consider the archerfish, a small fish found in the rivers and mangroves of Southeast Asia. The archerfish has a remarkable ability. It spits jets of water into the air to knock insects off of branches so that they fall into the water. In some sense, the archerfish is like a living model of a white hole. Instead of pulling things inward, it pushes them outward, ejecting a stream of matter into the environment. The insect, surprised, tumbles helplessly into the water where the fish waits. Just as the archerfish creates an outward jet, a white hole would create a cosmic jet of particles and light, pushing matter outward instead of drawing it in. Another example can be drawn from volcanoes on Earth. A volcano builds pressure underground and then erupts violently, spewing lava, gas, and ash into the sky. No one can enter into the core of a volcano while it erupts. The flow is strictly one way, outward. A white hole would be like the ultimate volcano of the cosmos, blasting matter outward from a hidden core. But unlike a volcano, which gathers its material from the magma beneath the crust, a white hole's material seems to come from nowhere, which is far more puzzling. Scientists have long been fascinated by such natural analogies because they make cosmic ideas easier to picture. A black hole is like a whirlpool in a river that swallows everything drifting near it. A white hole, then, would be like a hidden spring in the middle of the water that constantly gushes fresh streams outward, impossible to swim into. Over the decades, the debate has often shifted as new data arrives. In the 1970s, Stephen Hawking showed that black holes are not completely black. They can slowly evaporate by emitting what is now called Hawking radiation. This was a groundbreaking idea because it tied together gravity, quantum physics, and thermodynamics. If black holes can leak radiation, could they eventually die and in their final stage explode outward like a white hole? Some researchers think so. They imagine that at the end of a black hole's life, after trillions upon trillions of years, it might release all the energy it had swallowed in one great outburst. That would make it briefly behave like a white hole, but for now that remains theory. No one has lived long enough to see a black hole finish its life, and even the oldest stars we observe are not nearly old enough for their black hole remnants to have evaporated. This is why white holes remain in the realm of imagination, waiting for some sign that nature allows them. Even if white holes do not exist, the debate about them has been valuable. It has forced physicists to test the limits of Einstein's equations, to ask how time and entropy truly work, and to stretch their imaginations about what kinds of objects the universe may hold. It has led to new ways of thinking about the birth of the cosmos and about the connections between relativity and quantum theory. In this way, the very question, could white holes even exist, is already a tool for progress, whether or not the answer turns out to be yes. And so, the debate between theory and observation continues. Some researchers focus on refining the equations, exploring exotic models like loop quantum gravity or string theory, where white holes might appear more naturally. Others keep their eyes on the skies, hoping that one day a telescope might catch a strange flash of light or an unexplained burst of particles that points unmistakably to a white hole. Until then, white holes remain like legends whispered in the halls of physics, mathematical creatures that could exist but have not yet been found, always hovering between what the mind can imagine and what the eye can see. Where could a white hole appear? This question has occupied many scientists who think about the strange rules of space, time, and gravity. The term white hole itself describes something that is not yet proven to exist, but is drawn from the mathematics of Einstein's theory of general relativity. While black holes have been observed indirectly through their gravitational pull, their effects on nearby stars, and the X-rays emitted by material falling into them, white holes are still entirely theoretical. They're often described as the exact opposites of black holes. A black hole pulls matter in and allows nothing to escape, not even light, while a white hole would do the reverse by letting matter and energy out but not allowing anything to enter. Scientists ask where such a strange object could come from, and three ideas are often given. White holes might have been born in the very early universe. They might be tied to tiny quantum fluctuations in the fabric of space, or they could be connected to black holes as an extension of their structure. To talk about the first possibility, one must think about the beginning of the universe itself. According to modern cosmology, the universe as we know it began around 13,800,000,000 years ago. At that time, everything was compressed into an extremely hot and dense state, often called the singularity of the Big Bang. From that single event, the universe began expanding, and it continues to expand today. In those earliest fractions of a second, conditions were so extreme that the laws of physics as we usually know them may not have worked in the same way. Matter, energy, and space itself were unstable and constantly fluctuating. In such a situation, it is possible that white holes could have appeared as short-lived structures formed in the chaos of creation. Some scientists suggest that just as black holes can form from the collapse of massive stars, white holes may have been produced from the opposite process in the early universe, essentially erupting into being as explosive outflows of energy. These events might have been brief, lasting only a fraction of a second, but if so, they could have left behind effects that shaped the universe we see today. To explain further, it helps to remember what black holes are and how they form. A black hole is usually created when a very massive star runs out of nuclear fuel. Stars shine because nuclear fusion in their cores turns hydrogen into helium, releasing huge amounts of energy. This process pushes outward against the force of gravity that is pulling everything inward. When the star runs out of fuel, gravity takes over, and if the star is heavy enough, it collapses into an extremely dense point called a singularity. Around that singularity is the event horizon, the invisible boundary past which nothing can return. Astronomers have detected black holes in many ways, including observing stars orbiting invisible companions, detecting radiation from disks of hot gas spiraling into them, and recording gravitational waves from black hole mergers. But the same mathematics that describes black holes also allows for the possibility of white holes, which has led scientists to wonder whether such objects might be out there, hidden in some corner of the universe. If white holes really existed in the early universe, they might help explain some mysteries. For example, the distribution of matter in the cosmos shows clumps and filaments on very large scales, almost like a cosmic web. It is not fully understood how these patterns formed so quickly after the Big Bang. White holes releasing bursts of matter and energy could, in theory, have helped seed these structures, spreading material across space in unusual ways. In addition, some researchers propose that certain unexplained cosmic phenomena, such as fast radio bursts, extremely strong but brief signals coming from faraway galaxies, might be connected to white hole activity. These ideas are not proven, but they remain areas of active research because the early universe is still full of mysteries. The second major idea about where white holes could appear comes from quantum mechanics. Quantum mechanics describes the strange and unpredictable behavior of particles on very small scales. Space itself is not perfectly smooth at the smallest levels. Instead, it is thought to foam with tiny fluctuations of energy. These fluctuations can give rise to pairs of particles and antiparticles that appear and disappear in an instant. If space can create particles out of nothing through quantum fluctuations, some theorists wonder if it could also produce tiny white holes. These would be minuscule compared to the giant black holes we know, possibly smaller than an atom, and they might exist for only a brief time before vanishing. However, even if such micro-white holes last for only a short time, their existence would suggest that white holes are more than a mathematical curiosity. They could be natural products of the laws of physics. In this context, scientists sometimes compare the idea of micro-white holes to the concept of primordial black holes. Primordial black holes are hypothetical black holes that could have formed shortly after the Big Bang from regions of high density. These objects could be much smaller than black holes formed by stars, possibly ranging in mass from a single mountain to a planet. If primordial black holes are possible, then perhaps primordial white holes are also possible, born in the same early conditions of chaos and quantum fluctuations. Some researchers even suggest that certain phenomena we attribute to dark matter, the invisible substance that makes up about 85% of the universe's matter, might be explained if white holes or black holes of unusual kinds exist in large numbers. While this is speculative, it highlights the way white holes are used in theoretical physics to stretch the limits of our understanding. The third possible birthplace of white holes comes from their relationship with black holes. The mathematics of general relativity sometimes describes black holes and white holes as two sides of the same coin. In the simplest solution to Einstein's equations, called the Schwarzschild Solution, a black hole has a corresponding white hole on the other side of a mathematical extension. This suggests that in theory, every black hole might be connected to a white hole. If that were true, then white holes could appear not on their own, but as the other end of black holes. In such a model, matter falling into a black hole in one region of space could reappear coming out of a white hole somewhere else. This would make black holes and white holes part of a bridge through space-time, often described as a wormhole. Though wormholes are famous in science fiction stories, scientists have no evidence that they actually exist, and the conditions needed to keep them open may require exotic forms of matter that we have not yet observed. Nevertheless, the link between black holes and white holes is one of the most fascinating ideas in modern physics, because it hints at ways matter and energy might travel across space and time in ways we cannot normally imagine. To explore the black hole-white hole connection more deeply, one can look at the different types of black holes predicted by theory. The simplest black hole, the Schwarzschild black hole, is uncharged and does not spin. It is described by a solution to Einstein's equations that includes both a black hole and a white hole region. In this model, geodesics, the paths that objects or light follow through curved spacetime, can emerge from the white hole side. If one considers charged black holes such as the Reissner-Nordström black hole, or rotating black holes such as the Kerr black hole, the structure becomes even more complicated, and multiple connections between black hole and white hole regions appear in the equations. While it is doubtful that these perfect mathematical structures exist in the real universe, they provide a framework to think about where white holes might appear if nature allows them. Another aspect worth discussing is how long a white hole could survive if it did appear. A black hole can last for billions or even trillions of years, slowly losing mass through a process called Hawking radiation, named after physicist Stephen Hawking, who predicted it in the 1970s. In contrast, a white hole, by definition, cannot take in matter. Once it has expelled whatever energy it contains, it may vanish. This means that white holes might be inherently unstable, appearing briefly and then disappearing, which would help explain why we have never observed one. However, some researchers have speculated about more stable white holes. For example, a proposal exists that black holes at the end of their lives might explode and release all the information and matter they contain in the form of a white hole. In this scenario, the final stage of a black hole would not be total disappearance, but a transformation into a white hole that bursts outward. If that is true, then white holes could appear at the end of black hole lifetimes, which may be unimaginably far into the future. Because the discussion of white holes is so deeply theoretical, it often intersects with ideas from quantum gravity, which is the effort to unify general relativity with quantum mechanics. Currently, general relativity explains the large-scale structure of the universe, while quantum mechanics explains the very small. They do not fit neatly together. White holes serve as a kind of testing ground for theories that try to connect the two. For example, loop quantum gravity, a theory that suggests space is made of tiny loops, predicts that black holes might bounce into white holes instead of collapsing into singularities. In this view, matter falling into a black hole is compressed to extremely high densities, but instead of disappearing into a singularity, it rebounds outward as a white hole. If this is correct, white holes could appear not only in the distant past or in quantum foam, but as natural stages in the lives of black holes. This raises another possibility. Could our entire universe itself be the inside of a white hole? Some scientists have suggested that the Big Bang, the event that started everything, might be understood as the expansion from a white hole. In this scenario, what we call the beginning of the universe could actually be the eruption of matter and energy from the white hole side of another structure, possibly linked to a black hole in a parent universe. This idea remains speculative, but it shows the power of white holes as a concept to help explore the most fundamental questions of existence. When thinking about where a white hole could appear, it is important to remember why we have never seen one. The main reason is that their behavior would be very unusual. A white hole would push matter and energy outward, but since it cannot accept anything in, it would be unstable in a universe filled with matter and radiation. Even a tiny collision with particles around it could cause it to collapse. This makes it unlikely that large white holes exist in today's universe. If they did, they would be visible as extremely bright, short-lived explosions. Some researchers wonder if certain unexplained gamma-ray bursts, which are massive releases of energy in distant galaxies, could be linked to white hole events. Gamma-ray bursts were first discovered in the 1960s by satellites, and they remain some of the most powerful explosions ever observed. While most gamma-ray bursts are explained by supernovae or merging neutron stars, there may still be room for exotic possibilities like white holes. White holes are also part of the conversation about information. One of the biggest puzzles in physics is whether information is destroyed inside a black hole. According to quantum mechanics, information cannot be destroyed. But if matter falls into a black hole and disappears into a singularity, what happens to that information? One possible answer is that white holes could release the information again. In this way, the black hole-white hole pair could preserve the laws of physics. While no one knows if this is true, it highlights how white holes serve as tools for exploring deep questions that connect cosmology, quantum theory, and the nature of reality itself. In order to make these ideas more relatable, scientists sometimes use comparisons with familiar animals or natural processes. For example, a black hole can be thought of as a predator, like a giant squid deep in the ocean, pulling everything nearby into its grasp. A white hole, by contrast, would act more like an animal that releases or spreads resources rather than capturing them. One could compare it to certain plants or even animals that scatter seeds or spores into the environment. An example from the natural world is the puffball mushroom, When touched, it releases a cloud of spores into the air, spreading them far away. In a similar way, a white hole could release matter and energy into space. Another animal that offers a loose comparison is the sea cucumber, which can expel parts of its internal organs outward as a defense mechanism. The white hole, like the sea cucumber, would eject material from inside itself into the surrounding environment. These comparisons are, of course, imperfect, but they help give an image of what is otherwise an abstract mathematical idea. If one looks at other parts of the animal world, the concept of outward release rather than inward pull also appears. The bombardier beetle, for instance, ejects hot chemical sprays as a defense. This insect stores separate chemicals in its body and mixes them when threatened, releasing a spray that can reach 100 degrees Celsius. The beetle survives the process and continues its life. In some sense, a white hole might act like a cosmic bombardier beetle, producing a sudden burst of energy from within. These examples show that even though white holes are difficult to picture, nature on Earth offers parallels of systems that release rather than absorb. To bring all of this together, the question of where a white hole could appear continues to be a frontier of science. Whether they were formed in the early universe during the first fractions of a second, whether they pop in and out of existence through quantum fluctuations, or whether they are connected to black holes through space-time bridges, they remain an open mystery. No telescope has yet detected a white hole, and it may be that they cannot survive in the universe we live in, but their role in theory is crucial. They push scientists to think about what is possible, to test the limits of general relativity, and to connect it with the strange rules of quantum mechanics. When Albert Einstein first presented his general theory of relativity in the year 1915, he offered the world a radically new way of thinking about space, time, and gravity. For centuries, gravity had been understood through the lens of Isaac Newton, who imagined it as a kind of invisible force pulling objects together across space. The apple falling from a tree and the moon circling around the Earth were explained by this mysterious force. But Einstein's vision was far more daring. He suggested that gravity was not a force at all, but rather the bending and warping of space and time itself. In his picture, space and time formed a flexible fabric, and massive objects such as stars and planets created dents and curves in that fabric. Smaller objects like planets or satellites simply moved along the curves that this warping created. This new way of looking at the universe was expressed in what became known as Einstein's field equations. These were a set of mathematical rules that linked the distribution of mass and energy to the shape of space and time. The equations were complex, but they were also remarkably elegant, and they promised to reveal truths about the universe that no one had previously imagined. However, hidden inside these equations were strange and puzzling possibilities, solutions that seemed more like science fiction than reality. Among these peculiar solutions were the ones that described black holes, white holes, and the bridges of space-time that later became known as wormholes. In the early days after Einstein published his equations, very few people fully understood their consequences. Even Einstein himself did not at first grasp the bizarre creatures that lurked inside his mathematics. In the year 1916, only 1 year after Einstein's work was made public, a German physicist named Carl Schwarzschild discovered an exact solution to the equations. Schwarzschild's solution described what would happen if all the mass of a star was squeezed into a single point. This solution showed that space and time around such a collapsed star would curve so strongly that nothing, not even light, could escape its pull once it crossed a certain invisible boundary. This invisible boundary was later called the event horizon. What Schwarzschild had found was the first mathematical description of what we now call a black hole. At the time, however, neither Schwarzschild nor Einstein believed that such an object could really exist in nature. The very idea of a star collapsing into a point of infinite density, what we call a singularity, seemed too absurd. Einstein himself argued in later years that nature would somehow prevent the complete collapse of a star, perhaps by using rotation or internal pressure to stop the fall. For many years, most physicists treated black holes as nothing more than odd mathematical curiosities. But as decades passed, the understanding of relativity deepened. Other scientists began to explore different solutions to Einstein's equations. In the 1930s, two American physicists, Robert Oppenheimer and Hartland Snyder, revisited the problem of a collapsing star. They showed, through careful calculation, that once a star of sufficient mass runs out of fuel, nothing can halt its collapse. gravity overwhelms all other forces, and the star's core continues to shrink until it forms a black hole. Oppenheimer and Snyder's work convinced many that black holes were not just a mathematical trick, but a physical reality. As physicists studied these solutions, they noticed something curious. The equations of general relativity are symmetric in time. That means if you can describe how something behaves moving forward in time, you can also flip the equations and describe how it would behave if time were reversed. If one solution to the equations describes a black hole, then, by reversing time, another solution should describe something like the opposite of a black hole. This opposite solution became known as a white hole. A black hole, by its nature, is a region of space where matter and energy can fall in but cannot escape. The event horizon acts as a one-way door. Once something passes through, it can never return to the outside universe. A white hole, by contrast, would be a region where matter and energy can only come out but can never go in. It would be like a cosmic fountain, constantly spewing out particles and radiation, yet completely closed to anything trying to enter. No astronaut or spaceship could ever cross into a white hole from the outside. While black holes have gained firm observational evidence over the past century, white holes remain purely hypothetical. No one has ever observed a white hole in the sky, and many physicists doubt that they could ever form in reality. Yet mathematically, they are just as valid a solution to Einstein's equations as black holes are. The connection between black holes and white holes becomes even more fascinating when we consider the idea of wormholes. In the year 1935, Einstein himself, along with another physicist named Nathan Rosen, investigated a solution to the equations that link two regions of space and time together. They found that under certain conditions, the equations allowed for a tunnel-like structure that connected one black hole to another, or a black hole to a white hole. This tunnel came to be known as the Einstein-Rosen Bridge, though later generations would more commonly call it a wormhole. The image of a wormhole is one of the most captivating ideas in physics. Imagine space as a two-dimensional sheet of paper. If you wanted to travel from one end of the paper to the other, you could simply move across the surface. But if you could fold the paper so that the two ends touched, and then punch a hole through, you would have a shortcut that connects the distant points instantly. In a similar way, a wormhole would act as a shortcut through space and time, allowing a traveller to cross vast cosmic distances in less time than light would take to travel the long way around. In theory, a wormhole could link a black hole to a white hole. Matter falling into the black hole might emerge from the white hole somewhere else, or someone else in the universe. The idea has inspired countless works of science fiction, from novels to films, yet in the world of physics the reality of wormholes is highly uncertain. Most calculations suggest that wormholes, if they exist, would be unstable. They would collapse too quickly for anything to pass through, unless some form of exotic matter with negative energy density could be used to keep them open. Such exotic matter has never been found, though quantum theory does hint at strange effects that might serve the purpose. When scientists imagine the possible existence of wormholes, they often turn to analogies to make the concept easier to grasp. One of the most famous comparisons is to an earthworm burrowing through an apple. The worm could crawl across the surface of the apple from one side to the other, which would take time. But if it digs a tunnel straight through the apple, it arrives at the opposite side much faster. In this analogy, the apple's skin is like normal space, while the worm's tunnel is like a wormhole through space-time. As strange as these concepts sound, they are grounded in the rigorous mathematics of general relativity. The Einstein field equations are not mere imagination. They have been tested and confirmed through many observations, from the bending of starlight by the sun in 1919 to the detection of gravitational waves in the year 2015. These equations allow scientists to explore possibilities that stretch the human imagination, revealing a universe far stranger than anything ordinary experience could suggest. The notion of black holes, white holes, and wormholes has also been deeply connected with the study of singularities. A singularity is a point where the equations of relativity break down, where density becomes infinite, and the laws of physics as we know them no longer apply. In the case of a black hole, the singularity sits at the centre, hidden from the outside universe by the event horizon. For a white hole, the singularity would be in the past rather than the future, like an initial explosion that spits matter outward. In some speculative models, the birth of our entire universe in the Big Bang has even been described as a kind of white hole event, though this analogy is not exact. The mathematics of wormholes is equally curious. The Einstein-Rosen Bridge, for example, does not connect two separate universes in a permanent way. It collapses so quickly that no information or matter can actually pass through. Later, in the 1950s and 1960s, physicists such as John Wheeler explored the idea of traversable wormholes, looking for ways that such structures might be stabilized. Wheeler also coined the term black hole in the year 1967, replacing earlier and less elegant names like frozen star or collapsar. Throughout the 20th century and into the 21st, new discoveries have continually reinforced the strange predictions of relativity. Astronomers have found strong evidence for the existence of countless black holes in the universe, from stellar mass black holes a few times heavier than the Sun to supermassive black holes millions or billions of times heavier than the Sun. These giants lurk at the centers of galaxies, including our own Milky Way, where a supermassive black hole called Sagittarius A sits about 26,000 light-years from Earth. In 2019, the Event Horizon Telescope released the first direct image of a black hole's shadow, a glowing ring of light surrounding the monster at the center of the galaxy M87, 55 million light-years away. The evidence for black holes is overwhelming, but white holes remain purely speculative. Still, they occupy a special place in theoretical physics because they remind us of the symmetry of Einstein's equations and the deep mysteries of time. If time can be reversed in mathematics, what does that mean for the arrow of time in reality? Why does the universe seem to move in only one temporal direction, from past to future, when the laws of physics appear to allow both? Some physicists have suggested that white holes might play a role in the life cycle of black holes. For instance, according to the ideas of Stephen Hawking, black holes emit a faint radiation due to quantum effects near the event horizon. Over immense spans of time, this Hawking radiation causes a black hole to slowly lose mass and eventually evaporate. In certain speculative theories, the final stage of this evaporation could resemble a white hole, explosively releasing the last of the trapped information and energy. No one knows if this really happens, but it illustrates how black holes and white holes may be connected in ways we do not yet fully understand. To appreciate the wonder of these ideas, one might compare them to the most extreme animals on Earth. Just as relativity reveals creatures like black holes that defy our normal expectations, the animal kingdom is full of species with astonishing abilities. Consider the pistol shrimp, which can snap its claw so quickly that it creates a bubble hotter than the surface of the sun, or the tardigrade, sometimes called the water bear, which can survive in the vacuum of space, withstand freezing and boiling, and live without food or water for years. These animals are real, yet they challenge our sense of what life can endure, just as relativity challenges our sense of what the universe can contain. The analogy can be stretched further. A black hole is like the deep-sea anglerfish, dwelling in the dark abyss where ordinary light cannot reach, swallowing anything that comes too close. A white hole, if it exists, would be more like the bombardier beetle, which expels hot chemicals in sudden bursts to ward off predators, a constant outpouring of energy that nothing can enter. And a wormhole might be compared to the migratory paths of birds like the Arctic tern, which travels tens of thousands of miles each year, finding shortcuts across the globe that seem almost magical to human eyes. By blending the imagination of physics with the wonders of nature, we can sense the scale of the mysteries that Einstein's equations continue to reveal. These equations, scribbled on paper more than a century ago, have opened doorways not only to black holes and white holes, but to questions about time, space, and reality itself. They challenge us to think beyond the surface, just as the strangest animals of Earth force us to expand our understanding of life. Time's arrow is a phrase used to describe the way time seems to move in only one direction. We do not experience time going backwards, we only feel it flowing forwards, from the past into the present and then into the future. This one-way movement of time has always fascinated scientists, philosophers, and storytellers. It becomes even more fascinating when we look at the strange possibilities predicted by Einstein's theory of relativity. Among these possibilities are the objects known as black holes and their mysterious counterparts, white holes. These two can be thought of as complete opposites in the fabric of space-time. A black hole is often described as the ultimate end, a place where time and matter come to a halt, while a white hole is imagined as the ultimate beginning, a place where matter and light are expelled rather than swallowed. To understand this strange pair is to explore the deepest mysteries of the universe, and in doing so, we see how time's arrow might not be as straightforward as it feels in our everyday lives. A black hole forms when a massive star runs out of fuel and collapses under its own weight. The collapse is so intense that not even light can escape the grip of its gravity. This makes the black hole appear as a dark region in space, a place that pulls in everything that comes too close. The boundary around a black hole is called the event horizon. Once something passes this horizon, it cannot return. It is as if the object has been erased from the universe as we know it. For this reason, a black hole is often described as an endpoint, a cosmic graveyard where stars, gas, dust, and even entire planets may meet their fate. By contrast, the idea of a white hole is almost the mirror image of this. Instead of pulling everything inward, a white hole would push everything outward. If a black hole is a trap that nothing can escape, a white hole is a fountain that nothing can enter. From the outside, it would look like a place where light and matter burst forth, but no outside object could ever fall in. In the strange equations of relativity, white holes appear naturally as the opposite solution to black holes. While no one has ever seen a white hole in the sky, the concept remains a powerful tool to think about time and space. If black holes represent endings, then white holes represent beginnings, and this duality connects with the larger question of why time itself seems to always move forward. This idea of opposites is deeply rooted in the way nature often works. We can think of the life cycle of animals to help make sense of it. Consider the monarch butterfly, one of the most well-known insects in the world. The monarch butterfly has a life cycle that clearly shows both endings and beginnings. It begins as a small egg, laid carefully on a milkweed leaf. From the egg comes a caterpillar, which spends its days eating and growing, shedding its skin several times. Then comes a remarkable stage, the chrysalis, where the caterpillar appears to have reached an end. Inside, its body dissolves and rearranges, as if it had fallen into its own kind of black hole, where its former self is gone. But after a time, the chrysalis opens and a butterfly emerges, colourful and alive, fluttering into the world as if born anew. In this cycle, we can see something like the pattern of black holes and white holes. The chrysalis is the ending of one form, like the collapse into a black hole, while the butterfly emerging is like the sudden outpouring of light and matter from a white hole. Nature shows us again and again that endings and beginnings are often deeply connected. Black holes themselves were once only mathematical ideas. Albert Einstein developed his theory of general relativity in the year 1915. Not long after, in the year 1916, the German physicist Karl Schwarzschild found the first exact solution to Einstein's equations. His solution described what we now call a black hole. At first, many scientists thought this solution was only a mathematical trick, not something real in the universe. But over time, evidence began to grow. By the middle of the 20th century, astronomers had found strange stars emitting enormous amounts of X-rays, far more than ordinary stars could produce. These turned out to be binary systems, where one star was feeding material into a black hole. The material would spiral inward, forming a disk, and heat up to incredible temperatures, releasing powerful X-rays before falling beyond the event horizon. What was once only a strange mathematical idea had become a real, observable part of the cosmos. White holes, however, have remained in the shadows of theory. They appear in the same equations that describe black holes, but they would work in the opposite way. Instead of swallowing, they would expel. Some scientists have even speculated that the Big Bang, the great event that began our universe nearly 14 billion years ago, might have been like a giant white hole. In that single moment, space, time, matter, and energy burst outward in all directions. In that sense, the Big Bang was the ultimate beginning, the mirror opposite of a black hole's ultimate end. This idea remains speculative, but it shows how the concept of white holes stretches our imagination and helps us think about beginnings in a new light. The arrow of time plays a central role in this discussion. In our daily lives, time's arrow shows itself through the process of entropy, the tendency of things to go from order to disorder. A cup may fall and break into pieces, but those pieces will never spontaneously gather back into a cup. Ice may melt into water, but water will not freeze itself into an ice cube in a warm room. These changes point forward, from past to future. Black holes fit neatly into this arrow since they act as one-way doors. Once something enters, it cannot return. White holes, however, suggest the reverse direction, as if time could run backward in a localized region of space-time. The connection between black holes and white holes shows how deeply tied our understanding of time is to the very structure of the universe. Animals provide another way to think about this. Consider the sea turtle, one of the most ancient creatures on Earth, with ancestors going back more than 100 million years. A female sea turtle returns to the beach where she herself was born, hauling her heavy body onto the sand to lay her eggs. For the hatchlings, the moment of digging out of the nest and rushing toward the ocean is a beginning, a white hole moment, an eruption of life into the world. But the journey to adulthood is filled with dangers, from predators to storms to human activities. Many do not survive, and their journeys come to an end, swallowed by the great challenges of the sea. In this way, the cycle of life echoes the cosmic dance of black holes and white holes, with every beginning tied to an ending, and every ending feeding into a new beginning somewhere else. Black holes are also deeply connected to the idea of singularities. At the very centre of a black hole, the equations predict a point where density becomes infinite, and the laws of physics as we know them break down. This singularity is hidden behind the event horizon, and no information from it can escape. For white holes, the singularity would be in the past instead of the future. It would be the source of everything that comes out, rather than the endpoint of everything that falls in. This reversal of roles makes white holes difficult to imagine, but it also shows how they serve as the conceptual opposites of black holes. Where one swallows, the other spews. Where one ends, the other begins. Together, they form a pair that reflects the very structure of time's arrow. In recent years, some scientists have suggested that black holes and white holes might even be connected. One idea is that when something falls into a black hole, it might reappear later from a white hole, perhaps even in another part of the universe or in another universe entirely. This would make black holes and white holes like tunnels through space-time, similar to wormholes. Such ideas remain unproven, but they highlight how the opposites of end and beginning might not be separate at all, but could be two sides of the same coin. If we look again to animals for a mirror of this idea, we can see it in the migration of monarch butterflies. Every year, millions of monarchs travel thousands of miles from Canada and the United States down to the mountains of Mexico. Along the way, generations are born and die. No single butterfly makes the full round trip. Instead, one generation ends its life's journey, like matter falling into a black hole, and the next generation continues forward, emerging like matter from a white hole, carrying the migration onward. The end of one becomes the beginning of another, and together they create a continuous cycle that spans continents and seasons. This natural cycle echoes the cosmic cycle scientists imagine between black holes and white holes. The fascination with these concepts also reaches into human culture. Writers of science fiction have long imagined white holes as gateways to other worlds, as sources of mysterious energy, or as cosmic birthplaces. Black holes have often been seen as terrifying, destructive objects, the ultimate end that nothing can escape. By setting them against each other, as opposites, we can tell stories not only about physics, but also about life itself. Every culture has myths about creation and destruction, about birth and death, about beginnings and endings. The scientific language of black holes and white holes offers us a modern way to tell those timeless stories, grounded in the mathematics of relativity but alive in our imagination. The second law of thermodynamics is one of the deepest and most reliable principles in all of science. It says that in an isolated system, the total disorder, which scientists call entropy, will always increase or at least stay the same. Entropy can be thought of as a measure of how mixed up and spread out energy becomes. When we burn a log of wood, the ordered chemical bonds in the wood break apart and turn into heat, smoke, and ash. That heat then spreads out in the air, making the molecules move faster. The neat structure of the log is lost, and in its place is a much more disordered collection of molecules. This is what the second law describes. The world always tends to move from order to disorder, from neat and concentrated forms of energy to scattered and mixed ones. Every melting ice cube, every rusting piece of iron, every star burning its fuel is following this same rule. Now comes a very strange and puzzling question. If black holes exist, and we know they do, then what about their theoretical opposites called white holes? A white hole is a hypothetical object in physics that behaves in the exact opposite way of a black hole. A black hole is a region of space where nothing can escape, not even light, because gravity is so incredibly strong. A white hole would be the reverse. Nothing could ever enter it, and instead, matter and radiation would only pour out of it. Imagine a cosmic fountain that sprays out particles and light endlessly while refusing to take in anything at all. Such an object would be dazzling and frightening to behold. But it also raises a huge question. Would the very existence of a white hole break the second law of thermodynamics? To understand why this is troubling, it helps to remember how black holes themselves fit into thermodynamics. For a long time, scientists thought black holes were simple, almost featureless objects. They seemed to swallow matter and energy without giving anything back. But in the 1970s, a young physicist named Jacob Bekenstein proposed that black holes must have entropy. His reasoning was simple but brilliant. If you drop something with entropy into a black hole, then the universe would lose entropy unless the black hole itself had some way of keeping track of it. Stephen Hawking then took this idea further and discovered that black holes actually radiate a faint glow of particles, now known as Hawking radiation. This meant that black holes do have a kind of temperature, and therefore they must also have entropy. In fact, the entropy of a black hole is not proportional to its volume, but to the area of its event horizon, the invisible surface around it. This was one of the most surprising discoveries in modern physics, linking together gravity, quantum mechanics, and thermodynamics. So, if black holes can be understood in the language of entropy, what about white holes? A white hole would be like a mirror image in time. Instead of swallowing matter and radiation, it would constantly spew them out. But here's the tricky part. If you run the equations of general relativity backward in time, you can go from a black hole to a white hole. Mathematically, both are allowed. Yet nature does not always follow what is allowed on paper. The second law of thermodynamics tells us that time has a direction, often called the arrow of time. We know a glass can fall and shatter into pieces, but we never see shattered pieces spontaneously jump back together into a whole glass. That would mean entropy is decreasing, which the second law forbids. White holes look a lot like the shattering glass being reversed. They would take what looks like disorder, random streams of particles flying outward, and somehow concentrate it into a precise, ordered history that leads back to the moment of their formation. This seems to fight against the one-way flow of entropy growth. Some physicists have argued that if a white hole were to exist, it would indeed break the second law. Imagine particles flying out of a white hole in a very specific coordinated pattern. In order for those particles to be so neatly arranged, the white hole must have decreased entropy. It would look like the universe has become more ordered instead of less. That would be shocking, because it would mean there is a place in the cosmos where the arrow of time runs backward. It would be like watching smoke unburn itself back into a cigarette, or hearing scrambled music suddenly rearrange itself into a perfect symphony. But other scientists suggest that perhaps white holes would not truly break the law, because entropy is not just about local order, but about the entire universe. If white holes exist, maybe they would be part of a larger cosmic balance. For instance, one theory says that every black hole might eventually turn into a white hole after an unimaginably long time. The black hole would first shrink due to Hawking radiation, getting smaller and smaller. Near the end, instead of disappearing completely, it might bounce and transform into a white hole, releasing everything it had swallowed in a final burst. If this were true, then the total entropy would still increase overall, because during the black hole's life, entropy grew enormously, and the final release would just be the last stage of that process. In this way, the universe's bookkeeping of entropy would remain safe. This idea connects to quantum gravity, the still mysterious theory that should unite Einstein's general relativity with quantum mechanics. Loop quantum gravity, a theory explored by scientists like Carlo Rovelli, suggests that space and time themselves come in tiny, discrete chunks, much like atoms of geometry. According to this picture, the collapse of a star into a black hole might not end in a singularity, an infinitely dense point, but in a kind of bounce. That bounce could then emerge as a white hole. If so, then a white hole would not be a violation of the second law, but rather the natural end of a black hole's life cycle. Entropy would not decrease, it would just shift from one form to another. Still, this raises fascinating puzzles. For example, what would the entropy of a white hole actually be? With a black hole, we know it is proportional to the area of the event horizon, but a white hole, being the time reverse, has no way for matter to enter. Does this mean it has no entropy? Or does it inherit the entropy of the black hole it once was? Some researchers think that a white hole would carry the same entropy as the black hole that gave birth to it, because the information that fell into the black hole is not lost, but stored in some hidden way and later released by the white hole. This connects to the famous black hole information paradox. When matter falls into a black hole, does the information about it disappear forever? Hawking originally thought yes, but later changed his mind. If information is not lost, then white holes could be the cosmic mechanism that ensures the information eventually comes back out without breaking thermodynamics. Now, to picture this more vividly, let's use an analogy from everyday life. Imagine you spill a cup of coffee on the floor. The liquid spreads out in a random stain. That spreading entropy is increasing. You would never expect the coffee to suddenly leap back into the cup. A white hole, however, would be like the floor stain suddenly gathering itself up, drop by drop, and returning perfectly to the cup without spilling a single drop. This is why white holes seem so unnatural. They behave in the opposite way of everything else we see. The second law of thermodynamics seems to forbid such behavior. Yet, the universe at its deepest levels may not always match our intuition. The equations that govern space-time are symmetric in time. They do not care about forward or backward directions. What breaks this symmetry is entropy, the fact that the universe began in a state of very low entropy. Ever since the Big Bang, disorder has been increasing. If the universe had started out in a high entropy state, maybe time would not seem to have a direction at all. In that alternate cosmos, perhaps white holes would not look strange. Interestingly, some cosmologists have wondered if the Big Bang itself was like a white hole. After all, the Big Bang was a moment when all matter and energy in the universe came pouring out of a single point, and nothing could enter it. That sounds very similar to the definition of a white hole. If that analogy is correct, then we might already be living in the aftermath of the greatest white hole of all. And if the Big Bang did not break the second law, then maybe smaller white holes would not either. The difference, of course, is that the Big Bang set the initial low entropy conditions, while a small white hole today would have to appear in a high entropy universe, which is much harder to reconcile. Let us bring in some numbers to make this even clearer. The entropy of a black hole with the mass of our Sun is about 10 to the power of 77 units, called Boltzmann constants. That is an unimaginably large number. For comparison, the entropy of the Sun's normal radiation is far, far less. So when a star collapses into a black hole, the entropy skyrockets. This makes sense, because the second law demands that entropy must grow. But if such a black hole later turned into a white hole and released everything it had swallowed in a neat, organized way, entropy would suddenly fall, which is forbidden. Therefore, for white holes to be possible, they must release matter in a way that increases disorder, not decreases it. In other words, the particles pouring out must look completely random, not neat and orderly. If that is the case, then entropy continues to rise, and the second law is saved. Some computer simulations have tried to model what such an event might look like. In these models, when a black hole shrinks to near the Planck scale, that is about 10 to the negative 35 meters, it might explode into a white hole. The burst of energy would be chaotic, filling space with a mess of particles and radiation. Far from decreasing entropy, such a blast would actually add to the disorder of the universe. From the point of view of an observer far away, it would look like a kind of cosmic firework, not a neat reversal of history. This again suggests that the second law might not be in danger after all. Yet despite these speculations, no one has ever seen a white hole. They remain purely theoretical. Black holes, by contrast, have been observed many times. Astronomers have imaged the shadow of the supermassive black hole in the galaxy M87, and they have detected gravitational waves from black hole mergers. White holes, however, leave no such evidence. Some astronomers have suggested that short bursts of high-energy radiation, like gamma-ray bursts, could be signs of white holes, but so far the data does not strongly support this. Until we find one, the question of whether they violate thermodynamics remains open. It is also worth remembering that the second law of thermodynamics is statistical. It does not say that entropy can never decrease. It only says that it is overwhelmingly unlikely. In principle, a glass of water could freeze while sitting in a warm room, but the odds are so small that it would take longer than the age of the universe to see it happen. Likewise, a white hole might not be impossible. It might just be fantastically improbable. The laws of physics allow them, but the odds of one forming naturally are so tiny that we are unlikely ever to see one. This makes them fascinating thought experiments, ways of probing the deepest principles of time, entropy, and the universe, but not necessarily real cosmic objects. New clues about quantum gravity. why such a collision could expose physics beyond relativity. When we talk about quantum gravity, we're speaking of one of the greatest mysteries of modern science. Gravity is the force that holds the planets in orbit around the Sun, that makes the oceans rise and fall with the tides, and that keeps us firmly on the surface of the Earth. But even though Isaac Newton described its mathematical laws centuries ago, and Albert Einstein gave us a deeper picture with his general theory of relativity in the early 20th century, gravity is still not fully understood. On the other hand, quantum mechanics describes the tiny world of particles and atoms with astonishing accuracy. Yet when physicists try to bring relativity and quantum mechanics together, they clash in ways that suggest something very important is missing. Scientists call this missing puzzle piece quantum gravity. Imagine two massive black holes, each many times heavier than our Sun, spiraling closer and closer together until they finally crash in a violent collision. Such an event shakes the very fabric of space and time, creating ripples known as gravitational waves. These waves were first detected in the year 2015 by the Laser Interferometer Gravitational Wave Observatory, also known as LIGO. The discovery confirmed Einstein's prediction from 100 years earlier and opened an entirely new way of observing the universe. But researchers believe that hidden in the details of such collisions may be clues about physics beyond relativity. Clues that could point us toward quantum gravity. To make sense of this, it helps to imagine a collision as a kind of cosmic experiment, something nature itself performs on a scale far beyond what human-made machines could manage. Our particle accelerators, like the Large Hadron Collider in Geneva, can smash protons together at energies reaching trillions of electron volts. But when two black holes merge, the energies involved are billions upon billions of times greater. These are natural laboratories, where the known laws of physics are pushed to their breaking points. And when the laws bend too far, they may crack, showing us the limits of relativity and the fingerprints of quantum gravity. Einstein's relativity tells us that gravity is the warping of space and time caused by mass and energy. It is a smooth, continuous description. Quantum mechanics, however, says the world at the smaller scales is grainy and unpredictable. It is full of jumps, probabilities, and particles popping in and out of existence. If space and time themselves are subject to quantum rules, then at the tiniest possible scales, what physicists call the Planck scale, about 10 to the power of minus 35 meters, space-time may not be smooth at all. Instead, it may look like foam, bubbling and flickering like the surface of boiling water. But no telescope or microscope can see anything that small. Only the most extreme cosmic events, like the collision of black holes or neutron stars, could reveal such hidden structure. Think about how animals help us understand hidden worlds. For example, the African elephant, one of the largest land animals alive today, weighs up to 6,000 kilograms and can sense vibrations through its feet from kilometers away. Elephants use this ability to detect distant thunder or the approach of other herds. In a way, scientists using gravitational wave detectors are like elephants listening through the ground. Both are sensitive to tremors that ordinary senses miss. Just as an elephant can pick up faint rumbles that tell a story about far-off events, physicists can pick up ripples in space-time that carry secrets from black hole collisions billions of light-years away. When LIGO and its European partner Virgo measure these waves, they record tiny changes in length, so tiny that they are smaller than a fraction of a proton's diameter. It is almost unbelievable that such precision is possible, but it has already been proven. These measurements give us the soundtrack of cosmic collisions. The signal begins as a low hum, rises in pitch and volume as the black holes spiral together, and then abruptly cuts off when they merge. General relativity predicts this pattern with incredible accuracy. But if quantum gravity plays a role, there might be subtle differences, tiny echoes, irregular vibrations, or sudden distortions in the waveform. Finding such anomalies would be like finding footprints of a new animal in an unexplored forest, proof that something unknown is there. Some scientists propose that black holes may not be exactly as Einstein described. Relativity says that when matter collapses past a certain point, it forms a singularity, a place where density becomes infinite and the laws of physics break down. But infinities are a sign that something is wrong with the theory. Quantum gravity might smooth out singularities, replacing them with something more physical. Perhaps instead of a sharp point, the core of a black hole is a fuzzy ball of quantum fields, or even a wormhole leading elsewhere. If so, then when two black holes merge, the final object might ring in a slightly different way than relativity predicts. These subtle rings, called quasi-normal modes, are being studied with great care. Other ideas suggest that black hole horizons, the invisible boundaries beyond which nothing can escape, might not be perfect. Relativity says they are smooth and absolute, but quantum theory hints at fluctuations. Some researchers have suggested the existence of firewalls, energetic barriers that could destroy anything crossing the horizon. Others propose fuzzballs, where the black hole is not an empty region but a tangled mass of strings, as string theory suggests. If such things exist, the collision of black holes might leave traces in the gravitational waves, like ripples from a stone dropped into a pond full of reeds and obstacles. Even neutron star collisions can provide hints. Neutron stars are the collapsed remains of massive stars, so dense that a single teaspoon of their material weighs billions of tons. When two neutron stars spiral together and crash, they produce both gravitational waves and light, gamma rays, X-rays, and even visible signals. In 2017, such an event was detected, linking gravitational waves with a gamma ray burst, and confirming that these collisions create heavy elements like gold and platinum. Quantum effects might also play a role in these extreme conditions, where matter is compressed to densities greater than anything achievable on Earth. But why does this matter to us far from these distant collisions? It matters because the unification of quantum mechanics and relativity has been one of the deepest goals of science for a century. Theories like string theory and loop quantum gravity have been developed, but none has yet been confirmed by experiment. If gravitational wave detectors or future observatories like the Einstein telescope or Cosmic Explorer find even the slightest deviation from relativity's predictions, it could point the way forward. It could be the first experimental evidence of quantum gravity, reshaping our understanding of the universe. The search for these clues is a bit like how certain animals search for food in difficult environments. Consider the pangolin, a unique mammal covered in protective scales. Pangolins hunt ants and termites, often hidden deep in underground nests or inside tree trunks. They cannot see the insects, but they know they are there, and they dig patiently with long claws until they find them. Physicists, too, cannot see quantum gravity directly, but they dig into the data from collisions, searching patiently for the hidden evidence. Just as the pangolin's persistence ensures its survival, the persistence of scientists may eventually reveal the hidden structure of space-time. It is also important to recognize how difficult these searches are. Gravitational wave signals are faint and easily lost in noise, much like a whisper in a storm. Detectors must be isolated from vibrations, shielded from environmental disturbances, and equipped with the most advanced technology. Even then, researchers must sift through mountains of data, separating genuine signals from false alarms. Yet history shows that persistence pays off. For decades, people thought gravitational waves were impossible to detect. Now, not only have they been measured, but dozens of black hole and neutron star collisions have been catalogued. Some theorists have suggested that collisions might even create echoes after the main gravitational wave signal ends. In relativity, the final merged black hole settles into a stable shape, ringing briefly like a struck bell before going quiet. But if quantum effects alter the horizon, the waves might bounce back and forth, producing faint repetitions after the main event. Detecting such echoes would be like hearing an extra beat in the rhythm of a drum, proof that something unexpected lies inside. A few tentative claims of echoes have been reported, though none are yet conclusive. The possibility of discovering new physics through these collisions is thrilling, because it could touch on questions as old as humanity itself. What is space made of? Is time continuous, or is it built from tiny pieces? What happens inside a black hole? Where did the universe come from? Are there hidden dimensions? Quantum gravity may hold the answers, and cosmic collisions may be the key to unlocking them. Think of the cheetah, the fastest land animal, capable of reaching speeds over 100 km per hour in short bursts. When a cheetah runs, it pushes its body to the absolute limit of speed, agility, and control. Scientists, too, push their theories to the limit, testing relativity in the most extreme environments possible. Just as the cheetah's speed reveals the pinnacle of animal evolution, the collision of black holes reveals the pinnacle of physical extremes. And just as observing a cheetah in motion tells us about muscles, bones, and energy, observing cosmic collisions tells us about the muscles and bones of the universe itself, space, time, and gravity. Future detectors promise to expand our reach even further. The space-based observatory LISA, planned for the year 2035, will orbit the Sun and detect lower-frequency gravitational waves from supermassive black hole mergers, events millions of times larger than those seen so far. These signals could reveal new details about how galaxies grow, how black holes form, and perhaps how quantum gravity operates on colossal scales. Meanwhile, pulsar timing arrays, networks of radio telescopes observing the regular signals of spinning neutron stars, are already hinting at a background of gravitational waves spread throughout the cosmos. Each of these methods adds a new way of listening to the universe, like adding new instruments to a symphony. To understand how revolutionary this is, remember that for most of human history, the only way we studied the universe was with light. Visible light from stars later extended to radio waves, X-rays, and other parts of the spectrum. Gravitational waves add an entirely new sense, one that lets us feel the universe rather than only see it. It is as if a person born deaf suddenly learned to hear. A whole new world of information becomes available, and hidden in that new world may be the whispers of quantum gravity. The idea that relativity might not be the final word is not an insult to Einstein's genius. On the contrary, Einstein himself believed that his theory was incomplete. He spent much of his later life searching for a unified theory that would bring together gravity and quantum physics, though he did not succeed. Today's scientists are continuing that journey, building on his foundation, just as Newton's laws were not discarded but expanded by relativity. The history of physics is a history of refinement, of seeing deeper and deeper into reality. It is tempting to think of quantum gravity as something abstract, removed from ordinary life, but in truth, the pursuit of fundamental knowledge often leads to unexpected benefits. Quantum mechanics, once considered strange and impractical, gave us semiconductors, lasers, and the computers and smartphones we rely on every day. Relativity, once a purely theoretical idea, is now built into the GPS systems that guide our cars and phones, correcting for the warping of time by Earth's gravity. If quantum gravity is discovered, who knows what new technologies might follow in centuries to come? To picture the challenge ahead, think again of animals, which often adapt in surprising ways to survive. The octopus, for example, has no bones, yet it can squeeze through tiny cracks, camouflage itself with changing colours, and even use tools. Nature finds solutions where human imagination might not. Similarly, the universe may hold answers in forms we do not yet expect. Perhaps space-time is woven from loops, as loop quantum gravity suggests, or from vibrating strings, as string theory proposes. Perhaps it is something no one has yet thought of. Collisions of black holes and neutron stars may be the first clues leading us to that hidden design. Matter is everything around us. The air we breathe, the food we eat, the ground we stand on, the stars in the sky, and our own bodies. Antimatter, on the other hand, is its mirror twin. It is made of particles that look just like those of ordinary matter, but carry opposite electric charges and, in a sense, opposite qualities. When the two come face to face, they do not just bounce off each other or pass by indifferently. Instead, they annihilate each other in a flash of energy. The question that many scientists ask is whether their properties, when brought together, would cancel out perfectly like opposite numbers in a mathematical equation, leaving behind nothing but radiation. The story begins with the smallest building blocks of nature. In the early 20th century, physicists were unraveling the structure of the atom. They learned that atoms are made of protons, neutrons, and electrons. Protons carry a positive electric charge, electrons carry a negative charge, and neutrons are electrically neutral. Then, in the year 1932, the English physicist Paul Dirac made a theoretical breakthrough. His equations, which attempted to describe how electrons behave according to the strange rules of quantum mechanics and relativity, revealed that there should exist particles identical to electrons but with opposite charge. That particle, discovered soon after in cosmic ray experiments, was called the positron. It is just like the electron, but instead of having a negative charge, it carries a positive one. This was the first clear discovery of antimatter. Since then, scientists have discovered or created many types of antimatter particles. Antiprotons, which are like protons but carry a negative charge. Antineutrons, which have no charge but differ in internal structure. And even entire atoms of antihydrogen, which are made from a positron orbiting an antiproton. These are not imaginary. They can be created and studied in powerful particle accelerators such as those at CERN in Geneva. But they do not last long, because the instant they touch ordinary matter, they are destroyed in a burst of energy. This is why, in the everyday world, we do not see antimatter lying around. The idea of cancellation is central here. Suppose you take a particle and its antiparticle and bring them together. Do they simply vanish, leaving nothing at all behind? That might seem logical if we imagine matter and antimatter as exact opposites. But in physics, energy cannot be destroyed. It can only change form. When an electron and a positron collide, they annihilate. But what emerges is not emptiness. Instead, their combined mass is converted into photons, particles of light energy, usually in the form of gamma rays. These gamma rays are extremely energetic, far beyond the visible spectrum, so in a sense the properties do cancel each other out because the charge is neutralized and the mass disappears, but something new is created. Pure energy in the form of radiation. One can think of it as a kind of perfect balancing act. The universe keeps careful accounts. If you remove matter and antimatter from the balance sheet, you still need to credit the energy column, and that energy appears as photons. In some cases, instead of photons, other particles can be produced depending on the conditions and how much energy is involved. For instance, high-energy annihilation events in particle accelerators can produce showers of quarks, gluons, or heavier particles, which themselves decay rapidly into more stable forms. But what about the larger question? If you had equal amounts of matter and antimatter, would they really cancel out in every possible way, leaving only light and no leftover matter? This is not just a laboratory curiosity. It touches on one of the deepest mysteries in cosmology. According to the standard model of cosmology, the universe began about 13,800,000,000 years ago in the Big Bang. In those first fractions of a second, unimaginable amounts of energy condensed into matter and antimatter in nearly equal amounts. If the laws of physics treated matter and antimatter perfectly symmetrically, then every particle of matter would have had an antiparticle partner, and they would have annihilated completely, leaving behind only radiation. That would mean no stars, no planets, no life, no us. Yet here we are, living in a universe made almost entirely of matter, with only trace amounts of antimatter observed in cosmic rays. This means that, at some level, matter and antimatter are not perfectly balanced. Their properties do not completely cancel in reality. There is a tiny difference, a small asymmetry, that allowed a surplus of matter to survive after nearly all the matter and antimatter in the young universe annihilated. Scientists call this problem the baryon asymmetry. For every billion pairs of particles and antiparticles that destroyed each other in those early moments, one extra particle of matter was left over. It does not sound like much, but it was enough to build all the galaxies, stars, and people. The search for why this imbalance exists is one of the greatest quests in modern physics. Experiments at large accelerators test whether matter and antimatter behave in exactly the same way under all conditions. In principle, their mass, lifetime, and other fundamental properties should be identical. So far, experiments have found no major differences, but some subtle asymmetries have been detected in the way certain particles decay, such as kaons and B mesons. This phenomenon is called CP violation, meaning a violation of the combined symmetries of charge and parity. It hints that the laws of physics give a tiny preference to matter over antimatter, though the effect observed so far is not large enough to fully explain why the universe has so much matter. When we return to the idea of cancellation, the story becomes richer. On the smaller scales, a particle and its antiparticle do cancel in terms of mass and charge, but they do not erase the totality of reality. Instead, their meeting gives rise to radiation, or sometimes other particles. On the cosmic scale, matter and antimatter did not cancel completely, or else the universe as we know it would not exist. Instead, some imbalance favoured matter just enough to leave us with the stars above and the ground beneath our feet. This idea has also sparked the imagination of writers and scientists alike. If antimatter could be produced and stored in large quantities, it could be used as a source of nearly unlimited energy. The annihilation of 1 gram of matter with 1 gram of antimatter would release energy equivalent to about 43 kilotons of TNT, which is roughly the size of a large nuclear explosion. That is because of Einstein's famous equation E = mc², which shows that mass and energy are interchangeable. a tiny amount of mass, when converted entirely into energy, produces an enormous output. For comparison, burning 1 gram of gasoline releases less than 50 kilojoules of energy, while matter-antimatter annihilation releases about 90 trillion joules. This makes it the most efficient energy source known in theory. Yet it is not practical, because producing and storing antimatter is incredibly difficult. At CERN, researchers can create antimatter atoms, but only in vanishingly small quantities, just a few atoms of antihydrogen at a time. They trap them using magnetic fields, because if the antimatter touches the walls of a container made of ordinary matter, it instantly annihilates. In 2010, scientists managed to trap antihydrogen atoms for a fraction of a second, and in later years they extended that time to minutes and then hours. But we're still talking about quantities so small that they cannot be seen with the naked eye. It is fascinating to think about what would happen if larger amounts could be brought together. If a small chunk of antimatter were released in a laboratory, it would violently annihilate with the walls, producing showers of high-energy photons and other particles. The gamma rays alone would be deadly. This is why antimatter is not just an exotic concept, but also a dangerous one. The energy of annihilation is absolute, with no waste and no residue, unlike chemical explosions that leave behind smoke and ash. Some natural processes produce antimatter as well. In thunderstorms on Earth, gamma rays can create positrons, which then annihilate quickly with electrons. In the cosmos, pulsars, rotating neutron stars, can accelerate particles to such extreme energies that they create showers of antimatter. Around black holes, especially in their accretion discs where matter is heated to millions of degrees, antimatter particles are also produced. These annihilations release gamma rays that astronomers can detect with telescopes. The presence of antimatter in such environments is another reminder that cancellation is not the end of the story, but part of the universe's dynamic energy exchange. Even the human body has fleeting connections to antimatter. Every second, a small number of positrons are created inside our bodies as a result of natural radioactive decay of potassium-40, an isotope present in our tissues. These positrons annihilate with electrons almost instantly, producing gamma rays. Medical science has even harnessed this phenomenon in positron emission tomography or PET scans. In this imaging technique, a patient is given a substance that emits positrons. As the positrons meet electrons and annihilate, the gamma rays are detected, allowing doctors to create detailed images of metabolic activity in the body. So the meeting of matter and antimatter is not just a distant cosmic event. It is also quietly taking place inside us and in hospitals every day. The notion of cancellation can also be examined in terms of forces. Matter and antimatter carry opposite charges, but they are both affected by gravity in the same way. Antimatter, as far as experiments have shown, falls down under gravity just like matter does. For a long time, physicists speculated whether antimatter might behave differently under gravity, perhaps falling upward. This would have been revolutionary, but recent experiments with antihydrogen at CERN's Alpha-G project in 2023 confirmed that antimatter is indeed pulled downward by Earth's gravity, though the precision of the measurement is still being refined. This means that the cancellation of matter and antimatter is not in every sense complete. Their charges cancel, but their gravitational mass remains positive, and when they vanish into energy, the energy itself still gravitates. This brings us back to the puzzle of why the universe contains matter at all. If matter and antimatter were perfect opposites, the cancellation would have been complete after the Big Bang. But subtle violations of symmetry prevented this. The fact that properties do not perfectly cancel is why we exist. The cancellation is local, happening in each collision of a particle and its antiparticle. But on the global scale of the universe, there is a leftover balance, a remainder, which we experience as the material cosmos. It is tempting to compare this to the lives of animals, because nature also has examples of opposites that sometimes cancel and sometimes coexist. Consider the zebra, a striking animal of the African plains. Its black and white stripes seem like opposites that cancel into a pattern, yet the result is not disappearance but a distinctive coat that helps it survive. Zebras live in herds, grazing on grasses, and their stripes may confuse predators or protect them from biting flies. In a similar way, matter and antimatter are opposites, but their meeting does not produce emptiness. Instead, it produces something new, just as black and white stripes produce a living, breathing animal that is more than the sum of its colours. The zebra, for instance, is not just decoration. Its stripes serve biological functions that scientists still study. When lions hunt zebras, the motion of a herd can create a confusing blur of stripes, making it difficult for the predator to single out one animal. Flies, which are attracted to animals with uniform coats, are less likely to bite a zebra, reducing the risk of disease. This is an example of how apparent cancellation, like black and white on a coat, instead produces survival advantage. Similarly, the cancellation of matter and antimatter produces not emptiness but energy, which powers cosmic events and medical technologies alike. When one looks across the savannas of East Africa, where zebras roam alongside wildebeests and gazelles, one is reminded that survival often depends on the balance of opposites: predator and prey, camouflage and exposure day and night. In physics too, matter and antimatter represent a fundamental duality, a balance that defines the structure of reality. The zebra can live up to 25 years in the wild if it escapes predators, while matter has persisted for billions of years in the universe, surviving its cosmic predators, the annihilation with antimatter, thanks to a subtle imbalance. So, the scenario of matter meeting antimatter is not just about cancellation, it is about transformation. Their properties, mass, charge, and spin, do cancel in the sense that the resulting photons carry no charge and no rest mass, but energy remains, and sometimes new particles emerge. On the universal scale, the properties do not cancel completely, and that tiny remainder is what allows stars to shine and zebras to graze beneath the African sun. When two black holes spiral into each other and merge, they can release more energy in gravitational waves during a fraction of a second than all the stars in the visible universe emit in light during that same instant. Imagine two invisible monsters circling one another at half the speed of light, drawing closer and closer until they slam together in a burst of unimaginable power. This kind of event does not send out flames or shockwaves like an earthly explosion. Instead, the explosion is hidden, silent, but its ripples in space-time travel outward for billions of years, eventually reaching us. By the time these ripples arrive on Earth, they have faded into faint whispers. Yet those whispers tell us not only that the collision happened, but also how massive the black holes were, how fast they spun, and how far away they lay. The first time humanity heard these whispers was in the year 2015. Two enormous detectors known as LIGO, which stands for Laser Interferometer Gravitational Wave Observatory, picked up the signal from a pair of black holes colliding over 1 billion light-years away. These detectors are vast structures stretching 4 kilometers in each direction, built in the United States in Washington and Louisiana. They use laser beams bouncing between mirrors to measure the tiniest stretching of space caused by passing gravitational waves. When that first signal arrived, scientists could tell that two black holes, each more than 30 times the mass of the Sun, had crashed into each other. In that single instant, they released energy equivalent to several suns completely vanishing into pure gravitational radiation. Albert Einstein had predicted such waves 100 years earlier, in the year 1915, when he published his general theory of relativity. Yet even he thought they might be too weak to ever measure. The detection proved him right in theory but wrong in doubt, showing that human technology could indeed listen to the universe at its deepest level. If we could somehow paint a picture of gravitational waves, it would not be like a beam of light or a cloud of gas. Instead, it would appear as a pattern of stretching and squeezing rippling outward, like the rings you see when you drop a stone into a pond. But instead of moving through water, these rings travel through space-time. And unlike water waves, which move the surface of the liquid up and down, gravitational waves move space itself. A perfect circle would be stretched into an oval one moment and then squeezed into a different oval the next. The effect alternates as the wave passes. If you placed a ring of small floating objects in space, a passing gravitational wave would make the circle first stretch along one axis and shrink along the other, then swap directions back and forth. To an observer, it would look like the circle of objects was pulsing like a cosmic heartbeat. These ripples can come from many different types of cosmic drama. The most famous are mergers of black holes and neutron stars. Neutron stars are the crushed remnants of massive stars that exploded in supernovae. They are so dense that a single teaspoon of neutron star matter weighs as much as a mountain. When two neutron stars spiral into each other, they release not only gravitational waves but also light, gamma rays, and streams of heavy elements like gold and platinum. In fact, scientists now believe that much of the gold on Earth was created in such neutron star collisions billions of years ago. The detection of one such merger in 2017 allowed astronomers to see both gravitational waves and light from the same event for the first time, confirming theories about the origin of heavy elements and the behavior of extreme matter. To help imagine gravitational waves further, it is useful to compare them with something more familiar in the natural world: the calls of animals that travel great distances. For example, whales in the ocean produce deep songs that can travel hundreds of kilometers underwater. The songs carry information about the whale's identity, location, and even mood. Similarly, gravitational waves are like the songs of the cosmos, carrying messages about distant events. But while whale songs move through water and can be heard with our ears, gravitational waves move through space-time and must be detected with ultra-precise instruments. In both cases, however, the waves are a form of communication, a way for far-off events to leave an imprint on the world far away. Among animals, elephants also provide a fascinating comparison. Elephants use infrasound, which is sound at frequencies lower than humans can hear, to communicate across several kilometers. These low rumbles travel through the ground and air, reaching other elephants far beyond normal hearing range. Just as scientists build special devices to detect the deep vibrations of Earth, they also build instruments to pick up the faint rumblings of space-time. Imagine an elephant making a soft call that travels unnoticed by humans, but is received by another elephant many kilometers away. Gravitational waves are like that, silent to us, but loud and clear to detectors like LIGO and its European partner Virgo. The beauty of gravitational waves lies not just in their existence, but in what they reveal. Before their discovery, most of what we knew about the universe came from light in its many forms: visible light from stars, radio waves from galaxies, X-rays from black holes. Each type of light told us something different about the cosmos, like the colors on a painting. But gravitational waves opened a brand new window. They allow us to sense the invisible, dark parts of the universe where light cannot escape, such as black hole mergers. With this new sense, humanity can now listen to the universe as well as see it. What would it look like to watch gravitational waves if we could speed them up or magnify them enough for human eyes? Imagine standing at the shore of an invisible sea. Suddenly waves begin rolling in, not in water, but in the invisible fabric around you. The ground beneath your feet stretches and compresses rhythmically. Distant stars in the sky seem to wobble ever so slightly, shifting positions as the wave moves through space. Time itself ticks a little faster, then a little slower, as though the universe is breathing in slow pulses. Though these effects are subtle, the patterns of the waves carry the signatures of their source, like fingerprints. A black hole collision leaves behind a short, sharp chirp in the wave pattern, while a neutron star merger produces a longer, spiraling wave that tapers off as the stars crash together. To further make sense of these cosmic ripples, think of a drum. When struck, the drum skin vibrates in complex patterns, sending out sound waves into the air. A skilled listener can tell not only that the drum was struck, but also how hard, where, and what type of drum it is. Gravitational waves are like the sound of the universe's drum being struck by cataclysmic events. Our detectors are the ears pressed against space-time's surface, listening for those deep, distant beats. The difficulty in detecting them comes from their faintness. Imagine trying to measure the distance between Earth and the nearest star, Proxima Centauri, to within the width of a human hair. That is the kind of precision required to measure gravitational waves. The instruments must be shielded from earthquakes, passing trucks, wind, and even the tiny vibrations caused by molecules colliding in the air. Despite these challenges, detectors continue to improve. Plans are underway for even larger observatories, such as the Einstein Telescope in Europe and the Cosmic Explorer in the United States, which will be more sensitive and able to hear gravitational waves from even earlier in the universe's history. Some scientists dream of detecting waves from the very birth of the universe itself. According to theory, when the Big Bang happened nearly 14 billion years ago, it may have sent out gravitational waves as space expanded rapidly. These primordial waves would carry clues about the earliest moments of existence, long before stars or galaxies formed. If detected, they could reveal secrets about how space-time itself came to be. Searching for them is like trying to hear the first heartbeat of the cosmos. Just as every animal has its unique call, every gravitational wave source has its unique pattern. Black holes produce one type, neutron stars another, and even spinning neutron stars that do not merge can create steady ripples. The universe is like a forest filled with hidden creatures, each making its sound. For millions of years, humanity was deaf to these calls. Only in recent years have we learned how to listen. Now, with each detection, we discover new wonders. It is as though we had been watching animals silently move in the forest, and suddenly we can hear their songs and cries, revealing their behavior and stories. Even though gravitational waves themselves are invisible, artists and scientists often create visualizations to help people imagine them. These images usually show two massive objects, like black holes, orbiting each other. As they spiral closer, ripples spread outward in concentric circles, colored to represent the stretching and squeezing of space. The closer the black holes come, the faster and more intense the ripples become until they merge in a final burst. The ripples then fade as they travel outward into the darkness, carrying the memory of the event forever. In the natural world, one could compare this to ripples in a pond after two large fish leap and splash together. The waves spread out across the water's surface long after the fish disappear beneath. If someone far away saw the ripples reaching the edge of the pond, they could guess that something dramatic had happened at the center, even without seeing the fish themselves. In the same way, gravitational wave detectors on Earth see the ripples, without seeing the crash that made them. The study of these ripples is still young, but already it has changed our understanding of the universe. Before 2015, black hole collisions were only theoretical. Now they are confirmed realities, recorded dozens of times. Each detection adds to a growing catalogue of cosmic events, like an encyclopedia of the universe's greatest dramas. In the coming decades, detectors in space, such as the planned LISA mission by the European Space Agency, will be able to sense gravitational waves at lower frequencies than Earth-based detectors, opening another dimension of discovery. LISA will use 3 spacecraft forming a triangle millions of kilometers wide connected by lasers to measure space-time ripples. With such instruments, scientists hope to hear not just black holes, but also the steady hum of countless smaller sources across the universe, creating a cosmic symphony. If one wishes to imagine gravitational waves not as abstract ripples but as something tangible, it may help to think of them as invisible tides. The Earth already experiences tides caused by the pull of the moon and the sun, where oceans swell and fall in gentle rhythm. Gravitational waves, however, are not limited to the oceans. They wash across the very structure of space itself. Every atom, every mountain, every cloud, and every creature experiences this rhythmic stretching and squeezing, though by amounts so minuscule that life carries on without noticing. Yet the universe notices, and the waves faithfully carry their stories across unimaginable distances. Suppose you were standing on a great plain, watching a herd of wildebeest run in Africa. As thousands of hooves strike the ground, the vibrations travel through the earth as seismic waves. Even if you closed your eyes, you could feel the trembling of the land beneath your feet, telling you of the herd's movement. Gravitational waves are like the stampede of the cosmos, except instead of shaking the ground, they ripple through space-time. To instruments sensitive enough, the merging of 2 black holes is like the thunder of countless hooves echoing across the galaxy. The strange beauty of gravitational waves is that they carry not only the energy of the event but also its memory. They preserve the details of mass, spin, distance, and even orientation of the objects that produced them. Imagine hearing the cry of a wolf deep in a forest. From the pitch and tone of the howl, you could guess whether the wolf is large or small, young or old, near or far. Gravitational waves carry this kind of encoded information only about black holes and neutron stars. Each ripple is a howl from the deep wilderness of the universe, allowing us to identify the unseen creatures of space-time. When the first detection happened in the year 2015, it was more than just a scientific achievement. It was as though humanity grew a new sense, like suddenly being able to hear after living in silence. Before, we relied only on light in all its forms: visible light, radio waves, X-rays, gamma rays. But now we can hear the vibrations of space-time itself. It is the difference between watching a storm from far away through glass and stepping outside to feel the rumble of thunder beneath your feet. The discovery has transformed our picture of the universe from a silent movie into one filled with sound, rhythm, and texture, If one wanted to draw gravitational waves in a simple sketch, one could begin with two massive objects circling each other. Around them, concentric ripples would spread outward like water circles after a pebble is thrown. These ripples would not fade into flatness quickly, but would keep moving across the entire canvas, reaching every edge, however distant. Unlike water waves, which rise above the surface and sink below, gravitational waves alternate between stretching space in one direction and compressing it in another. A square drawn on the canvas would repeatedly morph into a rectangle one way, and then the other, pulsing in time with the waves. The image would look like breathing geometry, shapes rhythmically shifting as though alive. Consider how birds sometimes produce wing beats that cause ripples in the air. A swan gliding across a lake leaves behind not just a trail of water, but also a disturbance in the air above felt by nearby creatures. Gravitational waves are disturbances left by celestial wings beating through the darkness. They do not travel through air or water, but through the very grid of existence. If we could see them, perhaps the night sky would never appear still. Instead, faint shimmers and quivers would run across the stars, betraying the silent music of the universe. Let us linger on comparisons with animals, because nature offers rich parallels. Take the humpback whale, whose song can travel across entire oceans. The sound waves pass through seawater, bouncing and bending, reaching whales thousands of kilometers away. For scientists, listening to these whale songs reveals not only the presence of a whale, but also its emotional state, its search for a mate, or its connection to a group. Similarly, gravitational waves are the universe's songs, echoing across billions of light years. Listening to them tells us what kind of cosmic singers created them, whether black holes, neutron stars, or even exotic objects we may not yet have imagined. One of the fascinating aspects of gravitational waves is their speed. They travel at the speed of light, meaning they are as fast as anything in the universe can possibly move. When two black holes collide in a galaxy a billion light years away, the ripples reach Earth a billion years later, arriving in perfect step with any light or gamma rays emitted at the same moment.